Hi everyone. Good morning, good afternoon, good evening, depending on where you're joining us from. So welcome to WebAssembly Live Extended. So we held a WebAssembly Live event back in September last year, and this is basically a continuation of that event. So today we actually have 4 talks and a panel discussion at the end. But first, we'd like to thank our sponsors. Bloomberg Engineering sponsored WebAssembly Live, and Outsmartly is also another sponsor of ours. So thanks Outsmartly. And Second State is our newest sponsor, and one of their engineers is with us today to give a talk. So our schedule for today is as follows. So there's going to be a talk from Tim McCallum at 2:15 p.m. BST, and that will be followed by Yuta Saito, who will be giving a talk about porting Swift to WebAssembly. And then we're going to have a coffee break for half an hour, and then we will be back at 4 p.m. BST for Connor's talk, building function-based server applications using WebAssembly. And then at 4:30 p.m., we're going to have a talk from Robert Abukahil, and it's going to be about WebAssembly and Simdi, a match made in the browser. And then after that, at 5 p.m. BST, we're going to have a panel discussion with some of the speakers and some of the speakers as well from this event, like Jay Phelps and Mitch Dickinson of Shopify. So we will be regularly organizing events around WebAssembly, and you can always check out our website, WebAssembly Live, to see what's upcoming. And also sign up for our newsletter so that we can keep you posted on upcoming events. Right, so I think at this point, I'm going to bring in Tim, who is our first speaker.
Hey. Hi.
How are you?
Yeah, good, thank you. Good.
Great. So where are you calling us from? Where are you joining us from today?
Joining you from the east coast of Australia, and just nearing midnight, so 11:07 p.m. So it's good to be up. Good to be with you.
Thank you for staying up to join us, live today. So your talk is going to be about what? Do you want to just give a brief background as to what your talk will be about?
Yeah, sure. So for the last year and a little bit, we were all over there in California at the WebAssembly Summit, and since we basically left that event, we've been working really hard for a year and a little bit, providing a whole bunch of tools and tool chains for WebAssembly on the server side. And today's talk is about the path from on-premises infrastructure to zero infrastructure. So there's quite a big opportunity that WebAssembly brings to the table in terms of restructuring how you do IT, essentially, and how you deploy enterprise solutions and web apps. And we'll talk a bit about how that compares to traditional methods of, creating phone applications on operating systems and things like that, or creating very complex stacks to launch applications, as opposed to doing this very efficiently and effectively using WebAssembly with a lot less effort and a better result, to be honest. So it'll be an interesting thing to pull apart and discuss. Yeah.
Great. Looking forward to that talk. You also mentioned that your team has been, obviously, everyone these days have been working remotely, but I believe you, am I right in saying that this project started like just a year ago, and all this time you've all been working on this remotely, like nothing in person, or is that not the case?
Yeah, not necessarily. For me, it's been only remotely, being in Australia, and we've had some fairly comprehensive restrictions in lockdown and quarantine and things like that. But the team are based all over the world, so in mainland China and also Taiwan and the United States. And the other team members, they can all meet in in varying degrees and work in person or remotely. There's a whole host of things that Second State are working on, which I'll get to, I think, about halfway through the presentation. We're building some really fantastic software for a lot of different projects, for blockchain projects. And so we'll cover that very briefly. But today, mainly talking about how we've essentially over the last year gone from, understanding that a WebAssembly virtual machine has, for example, limited to like 4 data types, which are essentially integers and floats. And we've come from that time to now where we actually can process all high-level data types and build highly functional web applications using APIs. We've essentially exposed the WebAssembly virtual machine to the web layer, so people can just write web applications and call the VM. We'll go through the whole stack. There's a bit to go through. I hope I make it all in the 45 minutes.
I'm sure you will. And don't worry if you go over a little bit. That's fine. We've got
Sure.
a long coffee break, so I'm sure we can adjust
Okay.
a little bit.
Sure. Yeah.
I guess we can just get started. Obviously, it's a little bit early, like 4 minutes early in the schedule, but I think it should be fine. We're all obviously recording, this talk as well, so we will be making this available to everyone after the event. Once we've broken up, the individual videos. So I'm gonna just share your slides now, Tim.
Okay. Yep.
And I'm gonna remove myself from the stream so you can get started. So good luck on your talk, and everyone watching, I hope you enjoyed the talks we've got lined up for you today, and do join us for the panel discussion later on as well. Over to you, Tim.
Thank you. Thanks. Okay. Hey there, everyone. So yeah, as mentioned, today we're going to talk about the path from on-premises infrastructure to zero infrastructure, and specifically how we achieve that powered by WebAssembly. So as we know, the traditional on-premises infrastructure is quite costly in terms of both time and money. And some of the main drawbacks of on-premises infrastructure would include things like longer deployment times, more upfront capital expenditure, physical maintenance of plant and equipment, buildings, power generators, etc. Obviously, on-site staff are required. There's an element of cleaning, air purification required, physical safety requirements and things like that. Also cooling systems and so forth. So I'm sure we could all come up with a few more to add to that list. But to really make this point clear, if we take an example of, say, just one system in an on-premises outfit, say just one development machine on a sub-network, which drives development for, say, just one software project, we can see here that even in this micro environment, there's still many moving parts. So for this one system, we'll still have to install and configure and integrate and maintain things like an operating system, web server software, database, firewall, networking, and things like that. So as many of us who have worked in many projects would know, this whole process has to be done over and over, again, for different environments and obviously for each different project. So by now, I think we all get the point that it's fairly costly in terms of time and money. So moving forward, we really want to be looking for a new way to create highly sophisticated web applications without the need for any of this traditional infrastructure. So a new approach where the developers are able to create useful applications unfettered by these infrastructure headaches of the past. Of course, the arrival of virtual machines and the notion of containerization, and then ultimately the cloud computing, has certainly helped overcome the onerous tasks associated with that traditional computing architecture. Interestingly, even with the introduction of the cloud, studies have shown that once cloud computing becomes widely available, most enterprises only migrate around 20% of their operations from on-premises to cloud. In my experience, in large organizations and on large projects, there are actually some new barriers which surface when the migration to cloud commences. For example, it's hard for an existing on-premise operation to take everything into the cloud in one hit. It's near impossible, actually, because the business as usual activities can't really have any downtime. So as a result, one of the challenges is then trying to design integration points between on-premise and cloud systems as a migration is partially implemented over time. Another challenge is that there's multiple cloud providers, so choosing one is hard. Once interactions commenced, we see that each provider has unique proprietary mechanisms, which you kind of get locked into. So, for example, different storage APIs, different authentication APIs, different credentials and access control mechanisms, and different dashboards and user interfaces, and so on. So in some cases, a sophisticated project will actually put development time aside to create exit strategies in case they want to switch vendors. So, for example, while joining a cloud provider, they're at the same time writing migration strategies to exit that provider safely without losing any valuable time or data. So I personally think that WebAssembly is still very much underrated in the enterprise architectural landscape. But in saying that, I'm also very glad to see acknowledgements and things like this well-known tweet by the co-founder of Docker, which reads, if Wasm and WASI existed in 2008, we wouldn't have needed to create Docker. And that's how important it is. And he goes on to say that WebAssembly on the server side is the future of computing. So I have to agree with that. And I guess I'd like to add a personal thought on top of that also. The enterprise software market is absolutely huge, and the WebAssembly on the server is definitely a big part of that, potentially. Another phenomenal market is the mobile and handheld software and device market. And I personally think that if WebAssembly was around when the smartphone revolution hit, we would have probably built apps for the web. So, for example, web applications that run straight inside the browser, instead of creating multiple versions of the same app for each specific manufacturer's operating system, which means then also finding a way for manufacturers to disseminate those apps whilst keeping all of the users safe. The more I think about this, the more I think that there may have been chance that the app stores were never really needed and therefore possibly never invented. Let me explain further. If we're able to build sophisticated applications for the web, users would just access that functionality via their web browser on any device. So essentially, we're talking about a platform agnostic web application here. So first, let's think about this from the perspective of, say, a mobile application developer. So if we're looking at this from the developer's perspective, if we're creating a platform agnostic web, we essentially have no setting up of different development environments for each of the different operating systems, no building different installers for each of the different platforms, no submitting code to centralized entities for release approval, no pushing update reminders out to users, no relying on users to take their own time to update to the most current releases from us, the developers. And speaking of updates, pushing software updates to end user devices does increase the risk of these zero-day type exploits. For example, hackers can take advantage of bugs discovered in applications, say A, before the developer of the application can fix the newly discovered bug, or B, hackers can take advantage of bugs before the end user gets around to updating the software on their actual device. So we'll be looking closer into WebAssembly runtime soon, but just as I think of it, it's important to note that WebAssembly, we're actually able to do hot swap application logic in place. So this is actually a brilliant aspect of WebAssembly, where you can actually take a Wasm executable, and we'll show you how, whilst that's running in production, you can actually switch it out for an updated version, which will change the logic. The user doesn't actually have to take any action to make that happen. So it's a very different model. It's a different way of looking at it. So just talking a little bit about second state, just answering a question there at the start. So the second state virtual machine is a WebAssembly runtime. It's optimized for server-side applications. Now, it works seamlessly with existing application frameworks such as Node.js, but provides a secure and lightweight runtime at native performance. So it's a managed alternative to native code. It's ideal for building AI and big data microservices. We have a few examples of that coming up. The second state virtual machine also powers decentralized applications as the execution engine. So we're working on some leading public blockchain projects at the moment, like Ethereum 2.0, Ethereum Classic, Polkadot, the Web3, the Oasis, and also Cybermiles blockchains. So the main area that we're looking at today is really the zero infrastructure applications built on top and will dive into a diagram soon and have a look and unpack a bit of that. But it's just important to remember that Second State are working on a bunch of different projects for different applications, and this SSVM is essentially the engine that we're going to be looking at today. So I have this diagram here which helps illustrate essentially the suite of software. So this SSVM NAPI extension that you see at the very top of this diagram is a Node.js add-on. We can easily access this from a Node.js application, which is primarily what we'll be doing for the rest of this talk. This talk's mainly about examples of zero infrastructure applications, and we'll also do some examples of the lower level components, like if you can see there, the storage, etc. So in that plugin section, there's some TensorFlow functionality and some host storage functions and things like that. So we'll have a bit of a look at that. We also have some image processing functions that are built into this as well. So let's take a look at some examples of applications, prototypes, if you will, that you can build, which take advantage of this safe and very fast runtime environment. And we'll come back and dive a little bit deeper into the finer components of this. But for now, let's just have a look at some demos. So this is one of my favorites because it's something that I genuinely have needed when traveling. It's an optical character recognition and language translation demo, which runs directly in a user's browser. So to use it, you first take a photo of the menu or the words that you want to read. You select your preferred language options, and the application calls two API endpoints, one to perform the optical character recognition, the OCR, on the menu image, and then the other API can translate the characters to your choice of languages. And as you can see here, we perform OCR, and then the additional translation takes it from French to English. So it's important to know that this is not a phone app. There's nothing actually installed on the user's device whatsoever. The markup and JavaScript call the APIs, which are all executed inside the SSVM runtime, which we were showing on the previous slide. And the results of that execution are actually just sent back to the caller, so to the user's browser for display. This is a face detection demonstration, which takes an image, detects the faces, outlines them by editing the original image with the addition of the little green squares that you can see there. And then the image is returned to the user's browser as per the previous example. This is another example of the TensorFlow integration and the second state virtual machine, where users can classify insects via the API. And another one here, this image classification is the types of plants. So essentially, Second State have built all of the required underlying infrastructure to create almost anything that you can imagine. You just essentially build the front end to access the API endpoints. And we're going to show in a minute, you can actually create your own logic and deploy that up into the SSVM runtime. So let's dive in a little bit deeper now and get a good understanding of how you would create your own WebAssembly executable code as an API, and also wire up your front end to execute that code via the secure HTTP requests. So some examples of simple Rust code compiled to WebAssembly and then turned into a zero infrastructure application. All right, so this is an image processing demo which runs directly in a user's browser. As you can see here, there's a few different image processing options, including flip, brighten, grayscale, thumbnail, and so forth. So it's not a native application, and nothing has to be installed in order for the end user to use it. It's a web application which is running directly in the user's browser, and so essentially nothing is hosted. The client's JavaScript and markup are just talking directly to the APIs. So this kind of zero infrastructure application architecture is probably best described as what we call Jamstack. You may have heard the term Jamstack. This stands for JavaScript, API, and markup. The architecture is perfect for static websites, like the one we just showed you running straight inside the user's browser, essentially in a serverless fashion. So you may recall that we talked about the LAMP stack architecture earlier. And so obviously that consists of Linux, Apache, MySQL, PHP. This infrastructure is all required to host the web application. This is not the case with zero infrastructure applications using the Jamstack architecture. So with the Jamstack architecture, the web application is not necessarily hosted. The HTML and JavaScript reside with the user. Of course, it can be a static website. There's many tools around, but we won't cover those right now. We'll just stick to the raw JavaScript and HTML. So the zero infrastructure application is free to call any of the APIs for any computation. And the type of computation and the amount of computation is dependent on the application designer. So you can, like I said before, you can pretty much create anything that you can imagine. So let's also remember that the web application is a very general term. It does not have to be, you know, like a gimmicky image processing app. The application can be a full-scale enterprise application designed to keep remote connectors, you know, people connected via the web and things like that without having to actually run any complex infrastructure. I saw something the other day in the news, and I just created this slide. I think a fantastic use case for this type of architecture would be the prescription medicine dissemination in developing countries. So they're now trying to basically transition that from paper scripts to digital scripts and try and keep track of prescriptions and repeats and things like that. And I think it's interesting that each of the pharmacies would, in a situation where they're going to build this, would need complex native applications and run databases and servers and security, things like that. So you'd need a lot of synchronization between the units. In this type of design, where we'd have just really thin clients, the chemist would only really need to be able to access the state of the patient's scripts via a web browser. So all they'd need is essentially a text private key. And we'll show you a bit about that in a minute. So using the private key, the chemist can see what medication the patient has been prescribed and say how many repeats are left. And as soon as one chemist disperses one script and applies an update to the global state, all of the other chemists can now read that state. So in a situation like this, the patient would probably only need to have a mobile phone, like say a QR code, and perhaps some personal ID. Now, this is not decentralized, so this is not like a blockchain application. You know, the state is centralized in this situation, but the difference here is that the clients, so the chemists, they don't need any complex infrastructure to participate. There's no databases, like I said. There's no scripts that need to synchronize things at night and access each other via ports and things like that. They simply need some markup and some JavaScript and a key, and they can build a system like this, which would be quite secure, and obviously all the requests would be secure HTTP. So just an interesting use case that I think was simple, but I digress. So moving on back to the image processing. So let's look at a more concrete example here. So this application, we just reiterate, this is not hosted. It's actually on the client's file system. And so you can see this from the file protocol in the address bar. The HTML is presented straight from the user's file system into their web browser. And so this is the anatomy of a secure HTTP request. So first of all, we have the protocol, and then we have the base domain. So we have a system set up at the moment where you can write and deploy WebAssembly executables and execute them. So we'll do that in a second. We'll have a look at how we would do that. So that's the base domain. This is, of course, the port that's running on. And then we have here the path. Now, when you upload a WebAssembly executable to the system, it always returns you back an ID. So the next thing in this is the ID, the Wasm ID. Now, there's a convention that exists in that the Rust program that you, or the program that you write and compile to WebAssembly, the name of that will match the name when you're creating this call to the endpoint. So in this case, we've got a public function called rotate 180, and we also, as you can see there, rotate 180. And then the final thing there is the return type. Again, there's a convention. You can either return, say, a string from the whole operation, or you can return a byte array. So in this case, we're dealing with images. So at the end of the call, we put /bytes, and you can see in the corresponding WebAssembly, or the Rust, which will compile to WebAssembly, we are actually returning a byte array there. Okay, so that's pretty straightforward. So as we can see here, specifically this rotate 180 degrees function, the rotate 180 button will fire off some JavaScript, which will create a secure HTTP post request to a particular function, the one we just looked at before. So essentially the JavaScript's calling the API. Now, there's a whole bunch of examples and demos like this. These all come not only with live demonstrations, but also tutorials about how to write the Rust code, how to build and compile it to WebAssembly. So each of these examples, if you go to the secondstate.io/fast, you'll see a whole bunch of tutorials there, and it actually shows you how to, if you haven't already, install Rust and install the SSVM up tool, which is based on Wasm Pack, and it will show you how to write some Rust, compile that, deploy it up into the system, and then call those and various other things, which we'll cover in just a minute. So please check those out and see what new ideas for applications you can come up with. So I just want to mention inclusiveness for a minute, like openness. So with this particular system from Second State, anyone can build applications which access these APIs. So the depth and breadth of the applications and what each of the WebAssembly functions can do is only really limited to the creator's imagination. I have this image of a walled garden here because it's important to remember that sometimes we are in a walled garden, but we don't really know it. For example, when you're inside your social media app and you realize that if you logged out, you'd be completely isolated from everything and everyone inside the walled garden. There's a lot of applications that you really get immersed in, and you actually got quite closed in there. So this entire system that we're discussing here today is hosted on the open web. So there's no usernames, no passwords, no proprietary authentication. And also it's important to remember this is a cloud agnostic web service. So this is all just open web standards. Anyone can write the code, upload it, run it. And because of the sandboxed nature of WebAssembly, essentially like the sandboxed VM execution that we talk about, your code actually can't affect anyone else's code. And this means that in turn, your code is also safe. So here's some additional ways in which you can provide some custom behavior if and when you need it. So you don't want to be completely public. You can actually start making some tweaks. So let's have a bit of a look at that. So from a safety perspective, when you create and launch your WebAssembly executable, each of the executables is hashed into a checksum. And this hash is returned to the person who initially compiled and uploaded the executable. So the authenticity of the executables is able to be confirmed at any time with a simple secure HTTP request. As we can see here, that's just a GET request. We're asking for that particular executable at position 1, and we're using a filter to just return the checksum. And so we were talking before about executables and how they can be hot swapped. So this means that when a new executable is uploaded to that same Wasm ID, so essentially like a software upgrade or a patch, the new logic will of course run in place of the old logic. And this is a brilliant feature, which means that the application developer can update the application without the user needing to do anything. Cleverly, when a new executable is uploaded at that same ID, a new hash is also created, and this new checksum now provides authenticity for the new executable. So if at any point the application developer experiences a discrepancy in the checksum, they can take appropriate action. A test to confirm the correct checksum hash could be performed, say, inside the Zero Infrastructure app. So maybe that's hard-coded and that would need to qualify before it can call. Or perhaps, this is done from more of a centralized perspective where maybe there's a machine-to-machine API, maybe every minute or hour or something like that. The hash is checked just to make sure that it's authentic. So you can, obviously you could call the hash before, then run the function, then call it afterwards, things like that. And these calls are very simple and lightweight, so it's really not a big issue to go ahead and do that. So the exclusive access versus public access is an interesting point as well. So you can specify if you'd like to hold the keys to your Wasm executable. So how you do that is you are setting a parameter called create usage key. You're setting that to true when you're deploying the executable, and you're just doing this in the headers. And you can see there we've got some, I think it's can't see my screen under there. It's a curl command. And in the header, we have the SSVM create usage key set to true. And essentially what this does is it returns the usage key along with the, when it mints you the Wasm ID. It also provides that, as you can see down the bottom there, the checksum. It also provides an SSVM admin key. So we'll have a look at what that admin key is used for as well. I guess the key message here is when you deploy your executable, just make sure you grab the return values, so the admin key and your ID and so forth, because you're going to need that in the future to call and interact with your WebAssembly executable. So basically you can toggle between the private exclusive access versus the public access. So how you do that is you do a put request. Now you'll see there highlight is the SSVM admin key. So we're performing an admin operation here. So if we do a put request to that same WebAssembly ID, what we'll do is actually mint another fresh, unique SSVM usage key. So we're essentially flushing it. And so now we have a new key. The old users that were using the previous key will no longer have access. So this is useful in things like, I guess, if you're turning over people who are using it, maybe there's a class or a course where you have a cohort of students that use it, and then you basically flush the keys when they leave and generate new keys. So you're not actually replacing the Wasm executable, you're just refreshing the keys to change the access. And this is all, like everything in the system, it's all just done via secure HTTP requests. That's the only mechanism to interact with the system, which is great. Now we can also, if we want to make the executable just completely public, we can also use the delete verb when calling that same ID. And this essentially just flushes out the key altogether and returns a zeroed out usage key. Now, at this point, anybody who calls that WebAssembly ID, obviously with the correct function name and parameters, will be able to get the correct return value and take advantage of that logic that's executing there. So essentially, what we're going to talk about in a minute is like a pay-as-you-go model. So we have this notion of computation in the VM. We'll just have a look at this slide here. This is like a pay for what you use or pay-as-you-go functionality. It's made possible by the fact that Second State have built-in statistics mechanism, which measures the WebAssembly compute. So the monitoring of instructions, which are executed for a given function, they actually translate into what we call gas. And this is basically used to fairly distribute costs based on who's using the system. So this is essentially the fairest way to monetize a system like this. This makes total sense. So, heavy users, heavy computation, we get the statistics back. You can see there's an RPC request there for usage report. It'll tell you things like execution time and the total gas cost and things like that. So monetizing this, this is great for things like if you're trying to get investment and you're trying to explain that you've got costs associated, instead of having monthly bills or subscriptions or generic sort of fixed costs, you can basically explain that if the application is very successful and we have lots of daily active users and lots of hits, then we're going to be charged accordingly. And if the hits and interactions go down, then obviously the costs immediately go down. There's a complete correlation between those two things, which is fantastic. So approximately a year ago, we were just talking about this before we're looking at essentially the Wasm MVP at the time and discussing that it only supports these, integer and float data types. And so essentially what this means is that the WebAssembly stack-based VM is either pushing or popping any of these values to and from the stack. So the reason why this is important to bring up is that there's a decent amount of applications and they're going to want to pass around high-level data types in their function arguments. So we just go through this, mindful that I'm probably going to run out of time, so I'll try and speed it up a bit. So here's an example of where we actually use strings as part of the function parameters. So this Rust code here is compiled using the ssvm build command. And as you can see here, we submit a string and the Wasm VM performs the execution, and then we see a string return to the web browser. So this is just a simple hello world essentially, but we're actually processing strings and not those native integers and floats that we talked about before. So just to extend on that, we can pass in callbacks as part of the original request. So this trivial example shows how we can action a callback after the original function. And in this case, we're actually, the callback is that same hello world function. So instead of getting hello WebAssembly live, if we add the callback in, the first execution will work, and then after that we'll call that same function, and essentially the output is hello WebAssembly live. So that's a simple example of callback. Moving on from a trivial example, a real life use case would be something like sending an email or a text message via a third-party messaging service once the function is completed. So as you can see here, we've got the callback object, and in its header we've actually got the authorization. And this is important to understand that essentially we are passing in the authorization as part of the secure HTTP request in the headers. So if you have an account with a messaging app, your information is safe because you're sending the callback as part of the request, but that's all secure, and then that'll execute and then that terminates. So it's only for the lifetime of the request essentially. Okay, so let's have a look at, so the webhook functionality here is fantastic as well. So instead of actually requiring that the mobile device or that the zero infrastructure application provides, say, like an image in a watermarking application, we can actually perform a webhook function where the system will go off and fetch the image on the user's behalf, and then actually process that. So this is almost like it's a pre-execution fetch. And so to achieve correct ordering when we're calling functions, we simply add a suffix which consists of an underscore and a number, as shown here in this HTTP request. So using this convention, it doesn't really matter which order the data is collected from the web. So when it goes off to fetch an image, the system will ensure that the WebAssembly function is called A with all the function parameters in the correct order, and B only when the function parameters are in fact ready. So you can see there how you would send the request and how that correlates to the actual original function signature. So we talk a lot about WebAssembly stateless execution, but we also know that in order for an application to have usefulness beyond a single function, we need essentially persistence. So Second State have built in a permanent storage mechanism whereby every Wasm ID is allocated storage, and this storage key is abstracted away from the end user and the developers. This is one of the really interesting developments that we've discovered whilst designing technologies that go from the traditional on-premises infrastructure to zero infrastructure. So essentially we can store a series of I32, so Wasm compatible variables, as a blob in persistent storage. And the great difference here is that we are creating a new type of feature where a function has like a storage handle, and B, we're allowing the developer to store data without needing to manage any connectors. So developers are not having to instantiate, DB connectors and build, insert, and update queries and so forth. It's just fast, low latency storage. So these are some really great features that we've built in. We're actually able to send data right from the end user through to storage and keep that as low as we can, so not doing too many conversions. It's really efficient and effective. As you may have already guessed, that if you're using HTTP requests like the curl and the JavaScript, during this presentation, you should be able to use software, any software that can run with HTTP requests. So we've got some examples here like Ruby and Python and so forth. So it's extremely powerful. I think talking about enterprise applications, where we think of things like nightly workflows, automated batch processing, machine-to-machine communication and things like that. You can see how that we have a few different examples of these different programming languages. So ultimately, it doesn't always have to be, end user clicks and usage in that regard. It can actually be machine to machine communication and quite sophisticated back end server side work that's going on there, like maybe fetching images, performing alterations and moving them around, sending out notifications and things like that. So WebAssembly does really cover the whole gamut, doesn't it? From run it in the browser, run it on the server side, and then because those essentially you can create the application logic that can all be intertwined. So pretty much out of time. I'll give one little example I wanted to put at the end. This is just a little thing that I came up with a little while back. Just leave you with another zero infrastructure application idea. This one detects the pizza topping from a video in real time. So this is essentially the taking advantage of that TensorFlow component there. And we run a video and we let it analyze the images and try and detect the food there. And I think that's about all we got time for. So thank you for listening.
Yeah, thank you for that, Tim. You finished a little bit early. Okay, I'm just wondering if there are questions from the audience. We can actually take questions. So if people who are watching at the moment can type in questions on YouTube Live, we can take questions because we finished a little bit early. So just feel free to type in your questions. Okay. Someone's thanking you for the talk. Thank you for that. So feel free to type in questions for Tim if you've got any. Okay, so while we're waiting for questions, Tim, so if they want to find out more about the project, I'm guessing they just need to go to the website, right? Or are there any other things that you might want to mention about Second State? Like what you're doing, for example, for the developer community?
Sure. Yeah, so the best place to go, the starting point would be secondstate.io. And you'll see on the top menu, there's some different categories there. There's blockchain, serverless. You'll see the projects and affiliations we've got with different projects and companies around the world. So that's a really great place to go to start off. The links, if you go to the serverless tab, that's really essentially what we've covered today. And there's links off to a bunch of tutorials and demos. And it's really well explained. Everything's laid out in terms of if you're fresh to the system, each tutorial will start you off at the start. Have you installed Rust? Have you installed the tool chain? Here's an example of some Rust. So you can essentially follow a link to GitHub, and if you clone any of those demos, you can expand on them. So we've had a few things in the past, some little hackathons and things where people download the bones of the code, and then they extend on it and create different functionality. And that's essentially what I did with the menu translation app and the pizza topping app and things like that. You just basically grab something from the toolkit and try and use your imagination to come up with ways to extend that.
Okay, we actually have some questions here, so I'm just gonna show it on the screen.
Okay.
So the first question, can you see it, Tim? You want to maybe read it out and then?
Oh yeah.
Go on. Go ahead.
Have you ever tried the Wasm for video decoding playback? No, have not. Have not yet.
Okay. His follow-up question about that is, if yes, how was the performance?
Sure. Yeah. Yeah. No, that's something I would very much like to do, and I guess the thing, working on the server side, primarily because we're hosting, that rpc.ssvm.secondstate, where you can, the client can execute on the server. The server's execution time is really fast, and it's the issue is, I guess, with video, that you're sending the video to the server for processing and then back again. So there's that bandwidth overhead going up and back. We did some testing a while back on trying to find like a needle in a haystack. So having an enormous array of bytes, and then you have a little subset, and you're saying, is this needle in that haystack? And we can do that extremely quickly. But the issue that I faced is that you have to send the haystack and the needle to the server, and then so there's an overhead of bandwidth or that communication. So whilst there's some different nuances around the client server model. Obviously we have that remote fetching mechanism and things like that. So I haven't made any much video stuff a priority because of that. But there's some other great use cases that we're sort of focusing on first, but that I'd love to do that. And compression, decompression, I'm very interested in doing that, because you can run the same code on the browser and on the server. So you could really try and figure out some ways where you could take advantage of compression, decompression on both ends. Lots of things to explore.
Yeah, that's exciting. Lots of things happening. Okay, we've got another question here. Let me show it on the screen.
So what is special about WebAssembly in this setup compared to native code or other VM-based code like Java bytecode? So I guess essentially the great thing about WebAssembly is that when we're running it, it's running in that sandboxed environment. So you can actually use WebAssembly in a system where you can run untrusted code. So obviously, anytime you're running native code, you've always got that potential issue where you've got code that could interfere with other parts of the system. One of the big things about WebAssembly and the WASI side of things is that we're focused primarily on user safety by default from the outset. So by default, the WebAssembly VM can't access any of the system features. It's never going to turn your camera on or open a web connection or anything like that. It's very much compartmentalized in a very safe sandboxed environment. So that's a really huge advantage. Is you can actually, like we're doing, you have a system where anybody can write any code and upload it and execute it, and it's fine, because it's not going to affect any of the other people's code on the system, because everything's compartmentalized and sandboxed. So essentially what we do now is we start extending on that and building more and more functionality, but we're always focusing back on that user safety and a huge focus on that. So I guess to answer the question, compared to native code, the sandboxing is really the biggest thing. The VM-based side of things, I think one of the things, and this is still really from a research perspective, we're still working on this as well, but some good results, is this notion of like cold starts, like startup time. So we have ahead of time compilers. So when you upload your WebAssembly, now we actually run it through an additional compilation process, which makes an AOT file, which runs really, really fast. So the startup cold start times are negligible, and the execution is extraordinary. And so that's another interesting part of it, and that's why you can compare it to other containers and VMs and things like Docker, where you sort of bring into the conversation like things like startup and
Right. Yeah. Thanks for that, Tim. Just checking if there are any more questions. I don't see anything. So yeah, Tim. So thanks again for being with us today, and for staying up late.
That's okay.
To join the. Hang on a second. There's actually one comment here from Roberto Torres. Let me just put that on the screen.
Yeah, sure. So saying, I thought the idea of Wasm was to have it on the client. So the runtime on the client, you can obviously do that in the browser. We have WebAssembly on the server side as well. And what we're doing there is we're creating the RESTful interface essentially to execute server-side WebAssembly. So there's certain use cases where it has advantages. over it on the client side, and so it can be run on both. Yeah, and we do run it on both as well. There's we've got Dino, Node.js, there's JavaScript examples. There's a whole variety of things, and so today just essentially focused on the server side and the RESTful API, the Jamstack approach. Yeah.
Okay, there is another question here from Min. Okay.
Oh yeah, sure. So yeah, absolutely. There's a couple of different ways in which we can do this. So running a long-running task, we're looking at building in two different ways you can do this. One, you can actually specify that you want to wait for it to complete. And so essentially when it completes, you get acknowledgement in that same connection and that's resolved. And then the other one is if you want it to just run a long-running task, is you actually specify that you're happy for it to just go off and do it. And you're not necessarily wanting to keep anything open to wait for it to finish. It's a really good question. So we're actually heading towards developing this sort of functionality. The one thing you could do after a long-running task is you just add a callback object to it. So no matter how long that takes, eventually when it does finish, you'll get a text or some notification or an email or something will happen, whatever you design into it. But yeah, it's a great question because there are things that you might want to run which could take an enormous amount of time, like editing ginormous images or videos or something like that, and you don't necessarily want to sit there and if you close your browser, it's all over. So you might just want to push the button, shut it down, and then when it's finished, it'll ping you and say it's done. So that's, yeah, great question. We'll build that in. We have to build that into it just as a flag, yes or no. Do you want to wait or not?
So Min saying thank you for that reply.
Sure.
And there's also a comment here from this is really more for for me basically. Comment. It would be nice to repeat the question before answering for those not looking at chat. Yeah, I guess some people are multitasking and all that. So yeah, it's a good point, Richie. Thanks for that feedback. Any more questions? Not seeing any. Okay, so I guess we'll wrap up Tim's session for today, and we'll bring in the next speaker. Thanks again, Tim.
Thanks.
And if you can stay, otherwise enjoy your evening. I know it's very late there right now. So thank you very much again.
Thank you, guys. Okay, see ya.
Thank you. Let me bring in the next speaker, who is Yuta Saito.
Hi.
Hi, Yuta. How are you?
Oh, good.
Good. I hope the sound is not too bad because I had a problem with the sound earlier. Hopefully, it's not too bad right now. But yeah, thanks for again. I know it's late where you are. So where are you joining us again today?
I'm joining from Tokyo in Japan.
So thanks for staying up late. Like Tim, and joining us live because obviously it's sometimes better to have live events like this rather than recording it. But if unavoidable, we do record talks as well. So I'm just gonna bring up your presentation, and I know you're gonna be giving a talk about porting Swift to WebAssembly. This is gonna be very interesting to me because a few years ago I was running a Swift meetup group in London. And yeah, so this is something that I'm particularly interested in. I'm not gonna hold you up too much. I guess I'm gonna remove myself from the stream so you can get started with your presentation. And thanks again for joining us, Yuta.
Okay. So let's start. Hello everyone. Today, I'm going to talk about Swift Wasm, which is a compiler toolchain to compile Swift into WebAssembly using LLVM. First, I'd like to tell you about myself. I'm Yuta Saito, a university student in Japan, working at MailPay and a co-maintainer of Swift Wasm project. Of course, I'm also an enthusiast of Swift. So, why I like Swift and why I contribute to. First, Swift is designed for safety, preventing uninitialized variables, providing a flow checking, and automated memory management through automatic reference counting. And Swift is not only for iOS application, and it's designed to be capable for embedded system to server-side applications. And Swift supports object-oriented procedure and functional programming styles. This feature allows us to select the appropriate approach for the problem. And Swift is designed to be compiled to native code using LLVM, so Swift can achieve high performance at runtime. And the type system allows better semantic analysis, and it enables advanced optimization such as devirtualization. And Swift provides seamless interpretability with C, so it's easy to use with C library through FFI. And as you know, WebAssembly is portable architecture and binary format. And WebAssembly is already available on major browsers. It means that Swift targeting WebAssembly would essentially make Swift available in some form on all platforms that have browsers. And the web is a big developer community, so I hope porting Swift would increase developer population of Swift. Porting Swift to WebAssembly started with an issue in the Unscripted repository back in the 2014. While the Unscripted project was built as a backend for LLVM-based compilers, and Swift is built upon LLVM, so someone played around with Swift and Unscripted. Yeah, it's straightforward idea, but there are several problems, and the long story started from this issue. After a couple of years since the first issue opened, Patchend, Marx, and Zoe made great efforts around build system. And they published proof of concept of the port. The build system of Swift project is very complex. It's built by 15,000 lines of CMake script and 10,000 lines of Python script and 3,000 lines of shell script. So it's really incredible achievement. And since Swift standard library heavily depends on libc, so we had to polyfill them somehow. And they built standard library using Waji libc, which is a libc for WebAssembly programs built upon Waji system calls. After that, the Swift compiler can compile a simple Swift function. That was amazing news for me and motivated me to contribute to the project. However, the standard library does not work fine yet, and it crashes in almost all non-trivial Swift code. After a couple of months, I joined the Swift Wasm project and started hunting Wasm-specific bugs around compilers and standard library. As you may already know, WebAssembly is designed to be a secure architecture, so there are several limitations in instructions. And WebAssembly is still in the early stage, so it has some missing pieces. Therefore, we face two major issues while porting. The first one is relative pointer, and the second one is Swift-specific calling convention. Relative pointer is a pointer that has an offset between the address of the pointer itself and the target address. All pointers included in Swift metadata are represented as relative pointer. The offset is 32-bit, so it saves a lot of spaces on 64-bit platforms. It also saves roll-time relocation if dynamic linking is available. Yeah, but unfortunately, WebAssembly doesn't have such feature yet, so we can't get that benefit yet. Relative pointer is well efficient on most of platforms, but unfortunately, Wasm can't produce relative pointer at that time because it does not have a PC relative relocation type like ELF. So we need to replace all relative pointer with and metadata with absolute pointers. This needs a lot of efforts because there are many places where uses relative pointer. And it's quite hard to debug that because it's not clear where invalid pointers are produced. But as we expected, this replacement works very well. However, this workaround is temporary solution, and it only works on Wasm32 because the address size is not exactly same as relative pointer on Wasm64. The difference of pointer size would break the memory layout of metadata at all. So we had to address this issue radically. And I propose adding a new relocation type in the WebAssembly convention. It's very similar to the program counter relative relocation in ELF, but WebAssembly doesn't need PC relative jumping, so the new one is restricted to be used for only data segments. The proposal is now accepted, and implementations are already landed in LLVM. So I'm trying to use this in relative pointer now. The second interesting issue is related to Swift-specific calling convention. The calling convention defines how arguments are passed, how values are returned, registers guaranteed to be saved, or which may be overwritten. To support its language semantics, Swift defines a custom calling convention based on C calling convention. In the calling convention, the trailing two arguments are optional, and the caller can put additional argument even though the query function does not take them. This convention is designed to use registers to speed up error handling and passing context. And the mismatch of argument number between Corey and Cora is legal on existing architecture, since the Corey function just ignores the additional argument in registers. However, this LLVM-IR code will just crash when compiled to WebAssembly, because WebAssembly runtime validates that a signature specified by a caller should match the callee's signature when calling a function through function pointer. This validation is designed for secure execution. In this case, the foo is defined as a thread calling convention, and it takes two parameters. But the first call has three arguments. This call is valid on other architecture, but it's invalid on WebAssembly. This trick is used around capturing closure context and handling error exception in Swift. So I fixed the LLVM WebAssembly backend to emit dummy parameter in all functions, marked with Swift calling convention, and defined the calling convention for WebAssembly formally. In this case, foo is defined as Swift calling convention, and it only has two parameters without Swift attributes. So it's lowered with additional two parameters. Then the first call is now legalized, so it won't crash anymore. The second call is lowered with an additional argument. So the caller and callee signature are same now. So it's now valid call now. As I mentioned before, debugging Wasm program is really hard because there is no way to stop the program at breakpoint or dump memory space at a specific timing. Of course, Wasm time supports LLDB debugging using Dwarf, but it works on native binary compiled by just-in-time compiler. So it's impossible to execute instructions of WebAssembly step by step. And Chrome has an integrated debugger for WebAssembly, but it's rarely tied with a browser environment, and it does not understand Dwarf at that time. So I decided to develop an interactive debugger for WebAssembly. It's named Wasm Inspect. Wasm Inspect understands the Dwarf, and it enables source level debugging, and also it supports memory dump and step-by-step execution, and at WebAssembly level. This debugger has improved the debugging experience in WebAssembly significantly. After these kinds of bug hunting, we finally passed all test suites of Swift standard library. This means the toolchain is ready to run a somewhat complex application. So we started setting up toolchain distribution toolchain distribution and implementing some libraries to build web application using the toolchain. To make the project to be maintainable long term, we need to be able to replicate the build. Continuous integration is very helpful to identify which change causes regression. So we first set it up that CI that LLVM consumes a lot of disk space and a lot of time. So it's hard to find a CI service to allow that. But fortunately, GitHub Action allows 6 hours and around 50 gigabyte of disk space. So it enables us to build and distribute our toolchain continuously for multiple platforms. To demonstrate the state of the toolchain and enable to test FFI between JavaScript, we first made JavaScript interpolation library and named JavaScript Kit. This library allows us to interact with Web API from Swift. And it motivated us to build a UI framework on the web to build a practical application. So Max made a UI framework which is compatible with Swift UI and WebAssembly using the JavaScript Kit to communicate with DOM. Like this example, Tokamak allows us to build simple stateful web application using Swift UI APIs. As you can see, this Tokamak achieved to bridge event handler like button event. You can try this framework in path.swiftwasm.org. Please try it out. While developing a practical web application, we couldn't ignore its big binary size. The Swift standard library is a big single object file, and it's designed to be dynamically linked and shared with other processes, so it's really big. But unfortunately, WebAssembly doesn't support dynamic linking yet. So all Swift binary will include the whole contents of standard library, and it makes binary very fat. So I implemented a cross-module dead code elimination in compiler pipeline, and it reduces 60% of binary size while reporting the Swift to WebAssembly. The original Swift is also evolving. The Swift core team is now implementing concurrency feature in the language. The most popular feature is async await. So we are supporting that experimental feature to web. So how is the concurrency feature is implemented? If Swift has its own event loop, it works well on WASM environment, but it would be a problem when running on browser because it blocks the JavaScript thread. So the main UI thread will be glitched. As you know, JavaScript already has an event loop to run async jobs without blocking the thread. So we can use that to schedule async jobs produced by Swift. Let's see how this code works. First, when invoking a new JavaScript async function, in this case, the function is fetch. It returns a promise object immediately without blocking. And the await keyword in Swift code suspends the execution of this function. So this does not block the JavaScript thread. Then browser execute Web API internally. In this case, fetching web content from remote. Then, after the contents of URL fetched, the callback of promise is enqueued in JavaScript queue. And after the callback is dequeued and executed, JavaScript Kit will enqueue a new Swift job and schedule another JavaScript job to consume the Swift job in the next event loop. Then the JavaScript object will be invoked. The Swift function will be resumed. This is how the Swift concurrency works in JavaScript environment without blocking thread. This port is just getting started, and there is much more to do for the X system to grow. So there are many opportunities for others to get involved and improve it. For example, our toolchain depends on WASI API, so the produced binary always need to be run in WASI runtime or bundled with WASI profile script. So WASI-less bare metal target would allow the produced binary to be more portable. And there are more opportunities for performance and binary size improvement. The current binary include ICU for Unicode, and it is the biggest dependency of Swift standard library. If we can delegate it to the browser API and remove the ICU dependency, it would reduce a much binary size. As you can see, there are many interesting tasks. And as the X system is in its early stage, it's easy to make a contribution to this project. We are looking forward to your contribution. If you have a question or issue, please feel free to contact me. Finally, I would like to thank the many Swift Wasm contributors and sponsors. And Swift community helps us also. I'm deeply grateful. Thank you for your attention.
Okay. Thank you for that, Yuta. Let's see if there are questions from the audience. So people who are watching, if you've got questions for Yuta, you can type it in on YouTube Live, and we should be able to
Okay.
show it on the screen.
Okay.
So let's give them a few minutes. So how big is the team now, Yuta, that's working on Swift Wasm?
Okay. Mama, please.
Hi, Yuta, can you hear me?
Sorry, my internet connection is not good.
Okay. Right, sorry about that. So I'm just checking their questions here. Okay, lots of people thanking you for the talk. Thank you for that, folks. It doesn't seem like there's any question. Let me see. Oh, okay. Oh yeah, there is one from Azria. Then we show it on the screen. Do you want to just read out the question, Yuta, and then reply?
Okay. It's a dead code elimination performed based on some static analysis of wasn't worst code. How LVM didn't optimize not used part of code. Okay. The dead code elimination performed at a Swift level. Swift has its intermediate language named Shell, and my dead code elimination works at the Shell level, so it does not. So it can uses virtual function table information, so it can remove more functions based on LLVM. And the LLVM doesn't know Vtable, so it cannot eliminate some code. Yeah, so my language-specific dead code elimination works more efficient than the LLVM one. Thank you.
Okay, there's a question here from Joe Graham. Let me just bring it up. So what is the overhead of FFI calls?
Okay. Basically, WebAssembly is designed to be embedded with some host, so FFI calls should be implemented with cheap cost, and so it depends on runtime environment. But basically, WebAssembly does not provide some rich object passing like string, or some object like array or something. When passing those rich objects, we need to write it out in shared memory, so it consumes it has a little overhead when calling with FFI.
All right, so I'm just checking if there are any more questions. I don't think there is. So thank you very much again, Yuta, for joining us so late, where you are. And for everyone watching, so we're gonna take a 30-minute coffee break, and I've just displayed the talks that are upcoming after the break. So yeah, have some coffee, tea, and rejoin us again in around half an hour. Thanks again, Yuta. Okay. Hi everyone. So we're back from coffee break, and our next speaker is Connor Hicks. I'm gonna bring him in now so we can get ready. We can get ready with the slides as well. 1 second. Hi Connor.
Hello.
How are you? Let me
Doing well.
bring
How
in
are
the
you?
slides as well. Okay. Okay.
Seems to be.
Is it supposed to be like that?
No. It
Oh,
seems to be. Let me
can I
try something
refresh?
here. Yep.
No
I
worries.
will share my screen again. One moment. All right. Give that a try.
Okay, let me share that
There we go.
again. All right, that looks better.
Perfect.
Okay, let's just wait a few minutes in case people are just coming back to rejoin us.
Absolutely.
Because we did say 4 p.m. So, how has your day been? You're calling in from Ontario, right?
Yes, I'm in Canada. I am in Ottawa. Things are finally starting to get a little warmer. The Canadian winter is almost over, so it's lovely.
Yeah, same here. The weather is really great today, and I can see a lot of sunshine coming out. Coming in from from outside, and it's something to be out. Might have to go and have a bit of a walk after this event.
Yeah, absolutely.
Okay. So for everyone watching, again, you can ask if there's time. We can ask questions to the speakers. So just type them on YouTube Live in advance, so we can bring them in once the talk is over. Assuming there's time. Yeah, I'm sure we can have like a few questions. And yeah, so we'll deal with that later on. But do type in your questions ahead of time. All right, I think we can get started now, Connor. So what I'm going to do is I'm going to remove myself from the stream, and I'll leave you to together with your talk. And thanks for joining us again today.
Yeah, for sure. My pleasure. All right. Well, thank you for coming. My name is Connor, and I'm a staff developer at 1Password, and I'm also the creator of the Suborbital family of projects. And I'm going to be talking about building function-based server applications with WebAssembly. So before we get right into it, I just want to talk quickly about what is Suborbital. So hopefully my slides update properly here. The Suborbital family of projects is a set of open source libraries that allow you to build applications for the cloud. It allows you to build cloud native applications with less boilerplate and with a bunch of different capabilities that you normally have to build yourself. They're all written in Go, but they are designed to operate with WebAssembly as well. I'm really hoping that these slides update correctly. It appears that they are not. I may need to switch to a different browser here. Jen, could we maybe re-add something else to the stream from a different browser? I don't think this is going to work. Hopefully I can get these up and running nice and quickly for you.
Hi, Connor. Do you think it's from your end or the stream?
I've had problems with Firefox before, so let me try with a Chrome browser here. You should put those up on.
Maybe. Let's try that.
Okay.
Okay, let me share it again.
There we go.
That looks
So, yeah. So Suborbital has a couple of different projects under its umbrella. And it starts with Reactor, which is the job scheduler that powers everything at its core. And it allows you to schedule, Go, and WebAssembly jobs in an asynchronous manner. And it manages all of the inputs, outputs, and memory that is needed to make this work. Then we have Grav, which is a message bus, and the message bus allows you to send asynchronous messages both in process and among different instances on the network using plugins for discovery and for transport. So this means that Grav can discover other nodes on the network, as well as send messages between those nodes using a variety of different protocols. And then we have Vector, which is an HTTP framework for Go. And this allows you to build HTTP servers really quickly with not a lot of boilerplate, and it integrates really well with the other suborbital projects. And then we have Atmo, which is kind of the flagship project, if you will. And this actually combines the other three projects in a very particular way to provide a batteries included WebAssembly server development framework. So I'm going to go into a bit more information about Atmo during this talk. I'm going to give you a bit of a demo near the end, and then I'll hopefully answer any questions that you have. So let's get started here. And first I want to talk about the Sufa design pattern. Now this is something that I've been developing alongside Atmo. It is a way of designing server-side applications to make them scalable, easy to understand, and really easy to encapsulate code and structure your project in a way that will grow with what you're building and with your team. So to quickly run through the different portions of the Sufa design pattern, simple means that your application can be easily deployed to production. And so it's designed to work with a single auto-scaling group, for example. You shouldn't need a complicated deployment strategy in order to deploy an application that is designed with the Sufa pattern. Unified means that your application is built into a single deployable unit. And it is, you don't need to build dozens of Docker images or binaries or a whole bunch of different things at the end of your CI/CD pipeline. You can just build one single unit, and that can be deployed to production, on its own. And then function-based, I think, is fairly straightforward, but to be, kind of explicit about what it means is that your application's code is designed as a series of functions that can take inputs and provide outputs, doing some operations in between. And we'll see how Atmo uses these functions to build server-side applications. So, why WebAssembly? The project was actually originally based on Docker way back in the day when I first started it about 2 years ago. And as I worked through developing the project, it quickly became apparent that Docker was not the best way to build these really high-powered server applications the way that I wanted them to. The performance wasn't as good as I was hoping. The the execution of these containers just wasn't meeting my expectations. So I kind of took a pause and I started researching WebAssembly, and it seemed like it was going to fit the bill really well, and it turns out that it did. So the particular properties of WebAssembly that are important to me as I'm developing these frameworks is that it's portable, so it's platform independent. It can run on all sorts of different processor architectures, and it is secure. So the deny by default architecture that WebAssembly is designed for means that the host has to explicitly grant capabilities to a WebAssembly module in order for it to be able to do something, and that is a really desirable property when you're developing secure systems. And of course, it's fast. It is able to run code, at a very good level of performance. And this is always good as we're trying to build backend systems that scale and are able to handle lots of traffic. So starting to talk a little bit more about Atmo, Atmo allows you to write individual independent functions and compose them together to form the business logic of your application. We do this by creating a directive, which is a declarative description of what your application should do. And then we give all of this to Atmo, and we tell Atmo to run it somehow. So Atmo is actually figuring out how to execute your application at the time that it's happening, rather than you imperatively writing a program to execute the business logic. Atmo is going to figure it out for you. So if we take a look at that directive, it's a YAML file. It's pretty easy to understand, and it lets you describe how your application is put together. So the application shown here, this is one particular endpoint of a server. It's describing a home page endpoint, and it composes a set of functions together in order to satisfy requests sent to that endpoint. So, this particular handler that we're looking at here, we have a couple of different steps. The first step gets some users. The second step maybe fetches some posts. And then we have a for each operator that allows you to iterate over some posts, and for each post get some comments. And then we have a function group, which actually executes these three functions concurrently, I should say. So getting your friends, getting suggestions, and getting notifications can happen all at the same time. And then we have a final function that maybe renders the home page. So this kind of shows how you can write these individual functions, how Atmo will let you compose them together, and how the directive gives you the tools that you need to describe the business logic for your applications. This is really important because when Atmo is running in a production environment, for example, it is going to be cooperating with the other instances in your cloud infrastructure, and they may be communicating with each other. They may be executing functions over the network on each other using the Grav message bus. And by declaring what your application should be rather than imperatively writing it, you're allowing Atmo to intelligently decide how to execute these functions, and it can make the most of the resources available and make sure that things are getting scheduled in the right places. So I want to take a quick look at the architecture, the internal architecture of Atmo. And so like I said, Atmo is actually comprised of these other three projects. So Vector, Grav, and Reactor are all contained within the Atmo project. It puts them together in a very particular way that allows you to run your WebAssembly applications on the server. So when a network request is made, when a HTTP call is made to Atmo, it is received by an instance of Vector, and Vector passes execution to something called the coordinator. And the coordinator is what's reading your directive and instructing Atmo how to execute different handlers that you've described. So it does so by sending messages over Grav. So for every step in your directives handler, it will send a message over the message bus, and something at the other end is going to receive those messages. And that happens to be an instance of the Reactor scheduler. And so because these messages are being sent over Grav, and because Grav is able to actually either work in process or over the network, the function being executed might be on the same instance that received the HTTP request, but maybe the instance that received it doesn't have that particular function mounted at the time. And so Grav can actually send that over the network to another instance in your cluster that might have that function available already to so that you don't have to be downloading and loading these modules in real time while a request is happening. You can collaborate with other instances on the network to run these functions more quickly. So Reactor, whether it's in the same process or on a different instance, is receiving these messages from the coordinator, asking it to run functions as described in your directive. And it takes the input, passes it to your WebAssembly module, which we call runnables. And then that runnable produces an output, and Reactor will send a message back to the coordinator with the result. The coordinator will run through the steps in your handler, and for every function, as it provides an output, it actually saves that output to something we call the request state. So this is a set of key value pairs that are available to the other functions in the request chain. So if we look back at this directive, you can see that when the first function executes, we save the result of that function under the name user. And then when the, later down here, maybe when the get friends function executes, it needs to know which user we're getting the friends for. And so it can actually ask Atmo, please give me the value in state called user. And so it will be able to fetch the contents of this function's output to be used later down in the chain. And this is how we can allow the functions to be completely independent from one another, but still be able to chain together to form your business logic. So that's a bit of a look at Atmo internally. But I can talk about it for days, but it's always better to see something working in real life. So let's take a look at a quick demo. So over the weekend, I built this demo app. It's called Telescope, and it lets us look at some information about the repositories in a particular GitHub organization. So everything starts at the directive. This is the the structure of an Atmo application. The directive is the center of all of it. And this particular directive describes a couple of different endpoints. So we've got an endpoint for fetching a file. We've got an endpoint for listing the available repositories. We have an endpoint for fetching a particular repository. And we have an endpoint for creating a report, which we'll talk about in a minute. So this directive handler here, describes a get endpoint for the API v1 repos path, and it is saying call the list repos function whenever this endpoint is hit. So if we take a look at the list repos function, we'll see that this is a Rust runnable, and it will be compiled to WebAssembly to be used by Atmo. Atmo also supports Swift using the Swift Wasm project that we saw earlier before the break, and more languages are coming soon. So this particular runnable, it provides an implementation of the run function, which takes an input and provides an output. So this particular runnable here is reading a static file that we've provided to get a little bit of configuration to know which organization it is we're talking about. And that's provided here by the static directory. And the static directory is actually included in the application bundle. When you build your application for Atmo to run, anything in the static directory gets included in that bundle, and it gets mounted to the runnables as a static file system that they can read and get access to whatever's in there. So we're reading that configuration file, we're building a URL, we're making a call to the GitHub API here using the Suborbital HTTP client, and then we're using that information, we're deserializing it into a struct because we're filtering out fields that we don't necessarily care about. And then we're iterating over that list of repositories, and we're actually going to cache the value for each one to make it easier to access later. And then we are pushing that repo back out to JSON because we've filtered out some fields, so we need to turn that back into JSON with only the fields we care about. And then we were returning that JSON as the output to the function. So we've got this code, we've got our directive. What do we do with it? Well, Suborbital has a CLI tool called Subo, and we're going to use that to build our project. So Subo build with the native flag allows me to use the native toolchains on my machine. Subo actually ships with a Docker toolchain, which will use Docker images to build your code if you don't have the individual language tools installed on your machine already. But I do have those tools installed, so I'm going to use the native flag. So when I tell it to compile here, you'll see that it is going through each of the runnables in my project, like get repo, list repo, send report, and it is building them into a WebAssembly module. And then once it's built all of our runnables, it is taking all of our static files, adding them to the bundle, and then it produces this runnables.wasm.zip, which is includes all of our modules, our directive, our static files, and this is the deployable unit that I was talking about with the Sufa design pattern. This is all that Atmo needs to actually run your application. So I'm going to start a development server here locally using Subo. So if I run subo dev, that will start up a development Atmo server, and you can see that it's serving on port 8080. So why don't we go take a look at what this looks like. So I'll pull up an HTTP client here, and I'm going to make a call to that repos endpoint. So when I hit send, you'll see that we get a response back that contains the different repositories in the suborbital organization, and includes the fields that we care about: number of stargazers, the number of forks, and the number of open issues. And notice that it took about 360 milliseconds to make this request. We were talking to the GitHub API. There were multiple network hops involved. So, I guess that's fairly reasonable. But if you remember, when we looked at the runnable code, we were caching the repo information. So if I switch over here and I make a call for a specific repo using the v1 repo and then pass a particular name, we make this request, you'll see that we got that response back in just a couple of milliseconds because it's actually reading from that cache. So why don't we go take a look at that? So going back to the directive, our API v1 repo endpoint is being served by the get repo runnable. And if we take a look at what that runnable looks like, we will see that it is indeed accessing the cache. So it's doing some things that are similar to the previous runnable. It's looking up that configuration file to know which organization we're talking about. And then it is checking to see, hey, do we have this particular repo in the cache? If not, it is actually going to go and fetch from the GitHub API to get information about that repo. And then it will actually fill that cache back in behind it. So it's being a good citizen and filling in the cache whenever possible. You can see that we can set TTLs on those cache values. So the repo information will expire after 5 minutes. And then, but if it was found in the cache, then we are just returning the JSON from that cache. So that's why we were able to get a response so quickly and just single-digit milliseconds, because we were just reading from a cache. So that's great. And we have these two endpoints, listing repos and getting a particular repo. That's all good. But we want to maybe do something a little bit more complicated. So let's take a look at this report endpoint. So I've described a post endpoint to the API v1 report URL. And we've actually composed a couple of different functions together for this to happen. So the first step in this handler is a list repos function. It's the same list repos function that we called for this other endpoint here. And if we remember from the HTTP response, the output of that function is a JSON array of the repositories in the suborbital organization. So that's great, but we want to now use that information for something else. So we're going to save the output of this function to a state key called repos. And then we're going to use that for each operator that I talked about earlier to iterate over that array of repos. And we're going to do something for each one. So I'm saying for each element in the repos value, we're going to call the send report function. And I'm not going to show you what the function is yet. I want to do maybe a bit of a demo first. So I'm going to make a post request to that report endpoint. And what's going to happen is you're going to see some activity behind me in this other window. Oh, it looks like we've sent a report for repos to Discord using a webhook. So why don't we take a look at how that works? So if we open up the send report function over here, we will see that this is an iterating function. So we are using the special LM keyword to get the element of the array that Atmo was telling us to iterate over. We are taking the JSON of the particular repo in that array, and we are deserializing it into a struct. We're filtering out the repos that have less than 5 stars because, small potatoes, who cares about those? And then we are going back to that static file system, and we're asking for a configuration file called webhook, which you'll see in the static directory here. And that contains a URL for a Discord webhook. And then we are building a webhook payload. We're setting some headers on that request. And then we are actually making a post request to the Discord webhook URL to send that information. So if we go back to our directive, we're seeing that this function is being called on every element of the repos array. And so when that was executed, it iterated over this array of repos. And for any repo with more than 5 stars, it sent this little summary to Discord. So that's a nice way of composing several functions together, reusing functions across different handlers for different purposes, and using the control flow that Atmo, the directive, provides for you to make it easy to build applications. Now there's one last cherry on top that I want to show you. And so, remember that we have our Atmo server running down here on port 8080. And I'm going to switch over to my browser real quick, where you can see we have an address from port 8080 loaded up here. And if I hit go, you'll see that a little web app is loaded. And it's loading some information that looks fairly similar to what we were looking at before. So it's actually listing all of the repos under Suborbital, and it is showing us the number of stars that each of those repos has. And this seems a little bit innocuous. We're just making an API request, I'm sure, right? But what if I told you that this application was actually built using WebAssembly? So if we come back to our project and we look at the Telescope Web crate, we'll see here that we're using the U framework to build a single page application. So this U app, describes a home page. That home page contains some repos, and the home page gets rendered using those repos to display a list. And what's great is using the U framework, we can actually make API requests using WebAssembly. So this Rust code for this application, when it gets compiled down to WebAssembly, it uses the browser APIs to make network requests. And this API get repos function here is actually calling the API v1 repos endpoint from the Atmo backend. So what we effectively have here is a WebAssembly front end making API calls to a WebAssembly backend running here. And that makes this a full stack WebAssembly application, which I think is pretty cool. And what's even nicer is that when this application is built, the resulting files get put into the same static directory as our other two configuration files. So Atmo is actually serving everything that this front-end application needs, including the WebAssembly module that was generated by the U framework and the trunk bundler tool. So, we've got a WebAssembly front end, we've got a WebAssembly back end, and the final little piece of the puzzle here is when we look at how U is making this API request, you can see that we are returning this model repo struct as the result. And that seems a little bit familiar, because if we come over to the get repo runnable that's running on the back end, you can see that we are also using the exact same model repo struct on the back end. So we're actually sharing types between the front end and back end. And since they're both being compiled to WebAssembly, we get to share code unchanged between our client and our server. So I think that was a nice demonstration of the flexibility that WebAssembly brings, how it can run in a bunch of different environments, how you can share code between different environments running on different platforms using different execution engines. And that's it for my demo. And in fact, the end of what I have to show you today. You can visit suborbital.dev if you want more information about what it is Suborbital is all about. And you can follow me on Twitter at @cohicks. Yes, that's exactly right. So every function returns an array of bytes, which in most cases is JSON. And the Atmo coordinator saves each of those outputs to the request state object that is continually updated as your handler is executed. And then the functions further down in that chain can access that information. Since WebAssembly doesn't support complex types quite yet, there are, of course, proposals to make that happen. They're not fully implemented yet. Bytes is the best way for us to currently pass information between these different functions. One day when we have more complex data types, you'll probably be able to pass more complex data types. But for now, bytes formatted as JSON is the best we can do.
Okay, I don't see any questions and more. But Connor is going to be joining us the panel discussion at the end of this event. And the next speaker, Robert, will also be joining us there. So in case we miss the questions here, we will pick them up again during the panel discussion. So thanks again, Connor. I'm going to bring in Robert now, who is our next speaker. Right, so I think he's coming back. Okay, let's try that again, Robert.
All right, how about now?
Oh, that's
Does that sound
better.
better?
Yes, definitely better. Yep.
Good.
Okay, let me add your slides to the stream now. Thanks everyone for
Awesome.
bearing with us. Even I, we're having technical issues with my two laptops. Okay. So thank you for joining us, Robert. I'm gonna remove myself from the stream so you can get started with your talk, and then we'll see you at the other end for the panel discussion.
Sounds great. All right, thank you. Yeah, thanks everyone for tuning in. Today, I wanted to discuss WebAssembly and Simdi and how that can be a really powerful combination in the browser. Before I get started though, just a bit about myself. So my background is a combination of software engineering and bioinformatics. So in case you're wondering why a lot of the examples that I'm going to mention are bioinformatics related, that is why. So I'm an engineer at Invitae, which is a genetic testing company, and I'm the author of the book Level Up with WebAssembly. All right, so let's get started. So, when I think about what are reasons why people would want to use WebAssembly in the browser, two use cases come to mind. One of them is portability, and the other is performance. So when it comes to portability, whether we're talking about desktop applications or games or command line tools, these three are really good examples of large C and C++ code bases that we are now able to run in the browser thanks to WebAssembly. And what's interesting is that this portability story for WebAssembly is also extending outside the browser as well to things like serverless WebAssembly, as we've heard today, where you can essentially execute WebAssembly workloads through API requests and have them scale up and scale down and get all the benefits of serverless. And when it comes to performance, whether you're talking about image processing, machine learning, even browser plugins, all these three are good examples of using WebAssembly to speed up your web applications. And so this is kind of the context in which I want to kind of talk about Simdi, and really the question is like how do you use WebAssembly for improving the performance of your web apps? And so if you are building data intensive web apps, so for example, machine learning, image processing, audio processing, bioinformatics, here are a few ways in which WebAssembly can help. One is that you can find the slowest JavaScript computations and replace them with WebAssembly. So this obviously doesn't always work, but here are two examples from my own work where it's been really useful. So FastQBio and Ribbon, these are two bioinformatics web applications that let users do some data analysis directly in their browsers. And we were able to use WebAssembly to speed up the analysis anywhere between 3x and 20x. And in both cases, what we did was basically the same thing. We found an off-the-shelf tool that was kind of field standard tool that everybody uses, but on the command line. And so now we can bring it to the browser. And not only do we get better performance, we also got the benefit that this is a tool that is maintained and well tested and trusted by the scientific community to produce sound results. And so what's interesting about the performance aspect of WebAssembly is that it sometimes also ties in back to the portability aspect. All right, so another way in which you can speed up your web applications is multi-threading. So this idea that you can split up the work into smaller chunks and have background threads do the work in parallel. In the browser, the way this works is using web workers. So web workers let you execute JavaScript and WebAssembly in a background thread. And just a few caveats about this. So if your threads need to communicate with each other and have shared memory, the way you need to do that is to use something called a shared array buffer. Now, unfortunately, in 2018, the Spectre malware kind of forced browsers to disable access to the shared array buffer. And so for a while, you couldn't really do proper multi-threading with WebAssembly. And this is getting better. Like, it's already been several years now, and most browsers have turned back on that functionality. But just keep in mind that there's still about a good 30% of the web that doesn't have access to that, and that's where feature detection comes in quite handy. There are obviously ways to get around this. One reason why you would use multi-threading without sharing memory is if you just have a single thread. Now, this might not seem useful at all, but in the context of the browser, it could be very useful to farm out your analysis to one background thread, just so that your UI doesn't get bogged down and make a bad user experience. And the third one that I wanted to mention is Simdi. So let's dive into Simdi. So what is Simdi anyway? Well, Simdi stands for Single Instruction Multiple Data. And basically, you could think of it as a way of parallelizing code. So when we talk about multi-threading, we talk about taking a problem, splitting it up into smaller pieces, and then running those pieces in parallel. When we talk about SIMD, it's a different kind of parallelization at the CPU instruction level, meaning that we can run multiple computations within a single CPU instruction. So just to give you a concrete example, let's say we're looking at a three-dimensional space, and we're interested in calculating distances between two data points. And the way we're going to calculate that is using something called the Manhattan distance. And this is basically just adding up the differences in the respective coordinates of the points. So you can subtract the x coordinates, subtract the y coordinates, subtract the z coordinates, and then add up the differences. And that gives you a sense for how far apart these points are. For this example, let's say we just focus on the subtractions. If we wanted to do this normally, we would do 1, 2, and 3 subtractions, one after the other, and so 3 CPU instructions. With SIMD, what we can do is actually do those 3 subtractions at the same time. So we can take an extra large register on the CPU. Let's say in this case, we have a 128-bit register, and we store 4 32-bit integers in it. And so one point can be represented as a vector of x, y, z, and the other point similarly. And then SIMD will allow us to do this subtraction in parallel using a single CPU instruction. And that's kind of the general idea. And yeah, as you can imagine, this can significantly speed up your applications if you do a lot of math, if you do a lot of machine learning, image processing, what have you. So this is SIMD in general. How does this work in WebAssembly? Well, there are many flavors of SIMD, and WebAssembly does not support them all. Right now, the focus is on 128-bit SIMD operations. And one thing to keep in mind is that SIMD doesn't actually work in any browsers out of the box yet. So you'll need to turn on a flag, or in the case of Chrome, you can sign up for an origin trial so that your users on Chrome can still use it without tweaking the flag. All right, so what does this actually look like in practice? So as a test drive, let's take this library called SSW. This stands for Stripe Smith Waterman. This is basically just an algorithm that is very, very commonly used in bioinformatics for aligning two sequences to each other. So like if you have two DNA sequences, and you want to know how different or similar they are, that is typically the way that we do it. This library is an implementation of that algorithm in C, and it uses Simdi 128-bit. So we should be able to compile it to WebAssembly. And what I'm interested in is comparing the performance of having Simdi on versus having it off to kind of give us a sense for what are the benefits of enabling Simdi in the browser. So first, we're going to compile it to WebAssembly. To do that, I'm going to use the tool mscripten. If you ever do anything with C, C++, and WebAssembly, this is absolutely a fantastic tool. It does a lot of the heavy lifting for you. And so, for example, for this code base, this is the command line invocation I would use to compile it to WebAssembly. And so one thing you'll note is that it says em_make, and that stands for mscripten make. So it's essentially a wrapper around make, but for compiling things to WebAssembly instead of binary. And the other thing I'll do is add a Simdi flag at the end, and that will tell mscripten to add WebAssembly Simdi support. That's basically all I need to do. For this particular repository, it's that simple. In other cases, it might not always be. Some instructions are not supported yet, and this is still being worked on. And so, but now that we have that, what we can do just to verify that it did in fact compile to WebAssembly with Simdi enabled, we can look for these V128 instructions. And so all WebAssembly instructions that have to do with Simdi 128-bit will start with V128. And so now we can see we've successfully compiled it. Let's actually run it in the browser. And of course, it fails. And the reason it fails is because, as I mentioned, browsers don't enable Simdi by default. And so what you need to do is go in the settings, tweak the flags, and then you can actually run it in the browser. And so here we're seeing I'm able to run a command line tool that uses Simdi in the browser. And this is just showing the command line tool help screen. And so this tells us that the browser is in fact able to recognize these Simdi instructions. All right, so at this point, we have a .wasm file that has Simdi enabled. Let's try the other way around. If we wanted to compile without Simdi, surely that should be really simple. Just remove these Simdi specific flags. And no, that doesn't work. That's too easy. And the reason why this doesn't work is because this code base makes explicit references to Simdi instructions. So it uses these functions like _mm do stuff that you can't simply ignore. You have to tell the compiler, what do I do instead if I don't have Simdi? And so that can get pretty complicated, but thankfully there is this fantastic tool called Simdi Everywhere. It's not specifically built for WebAssembly. This is just a general tool for compiling things that need Simdi where your system might not support Simdi. And so this lets us compile to WebAssembly a getter Wasm binary that does not invoke Simdi instructions. So now we have those two. The next thing we want to do is actually compare the performance. And the way we're going to do that is we're basically going to align a bunch of sequences to each other and see how long it takes. See, on the x-axis, I'm going to show you the number of sequences aligned, and on the y-axis, how long it takes in seconds to run that. I want to compare 3 different things. One is native runtime. So how long does it take if I just run it in the command line without forgetting about the browser? And then I want to see what happens with WebAssembly and SimD, and then with WebAssembly but without SimD. So just as a thought experiment, before showing you the actual numbers, this is kind of what we would expect. We'd expect to see native performance. You know, the more sequences you align, the longer it'll take. Compared to WebAssembly SimD, we expect it to be pretty close to native performance, but not quite there. And this is something that we typically see anyway with WebAssembly. And then if we turn off SimD, what we expect is that the runtime will be even further away from native. And so this is what we expect. The actual results look a little different, something like this, where you can see that the native and WebAssembly SimD lines, the red and yellow lines, look pretty close to each other as expected. But WebAssembly without SimD is actually pretty far off. So we're talking a couple order of magnitudes away. And in fact, I stopped benchmarking it after 100 sequences because it started taking way too long. And one thing to keep in mind about this graph is that the y-axis is actually a log scale. So the differences are larger than they seem. And yeah, to me, this illustrates a few things. One is that, you know, while with WebAssembly, it makes it possible to take something written in other languages, bring it to the browser, combining it with SimD is actually going to make a lot of these processing applications much more feasible in the first place. And the other thing that's neat about this is, you know, when we talk about the performance differences between something that's written in JavaScript and WebAssembly, it's oftentimes possible to argue that maybe the JavaScript wasn't optimized enough. Maybe there's a way to tweak the JavaScript to make it as fast as WebAssembly. And what's neat about SimD is that for a specific class of applications, you know, it's getting us into a realm that JavaScript cannot actually access, right? We cannot run SimD operations on your CPU from JavaScript. And so this is really why I'm really excited for WebAssembly SimD to become enabled in all the browsers without flags. Yeah. And if you want to get started with SimD, there are just a few resources here. Feel free to take a screenshot of this. Again, if you're using C and C++ with SimD, Emscripten is a fantastic tool for that. Next, these are the browser flags that you can use to enable SimD in your browser. I also added links to useful libraries, so SimD everywhere, which is very useful, not just for benchmarking, but also, you know, you want your app to be available even for folks that don't have SimD enabled. And to do that test, you can use this really great library called Wasm Feature Detect. And so it lets you do things like, if SimD is enabled, load this binary, if not, do this other thing. And yeah, also added links to other articles relating to SimD. And yeah, if you enjoyed the contents of this talk and you're just getting started with WebAssembly, feel free to check out levelupwasm.com. I do also have a whole bunch of free articles and videos and resources that you can check out as well. And with that, I want to thank you very much for tuning in.
Okay, thanks. Right. There's a lot of like issues with sound today, unfortunately.
Yeah.
But that's how it is. It happens. Okay. I'm gonna see if we've got our panelists back. I know we've still got Connor, so I'm gonna bring him back in. And so there will be two other people joining us, Jay Phelps and Jay Phelps from Outsmartly. He used to work for Netflix and Citadel. And Mitch Dickinson works for Shopify. So hopefully they'll be joining us shortly. We finished a little bit early. So let's see if there are questions from the audience, say for Robert and Connor, with regards to their specific thoughts. Okay, there's one here from Azria. Let me bring that up. I'm not sure if this is okay.
Yes. So the question is,
so
nice performance boost. Oh, sorry.
Isn't enabled by default?
Yes. Basically the reason is because it's still being worked on, and it's very early on still. That's really all.
Okay, I don't see any more questions. So we're gonna have to wait a little bit until the two other panelists joins us. Oh, Mitch is already here, so let me add him to the stream. Hi, Mitch. Oh, he probably stepped away. So it's a little bit early. That's why. Right, let's see if Jay has joined. Okay, maybe I can ask Connor first. Connor, do you want to talk about your project? Because I know you were at one point we were chatting about you looking for people to either, I don't know, partner up or invest or something. Do you want to maybe just talk about that a little bit?
Yeah, I'm looking for contributors to come and work on the project with me. It's entirely open source. We are, trying to move a little bit quicker. I've got a couple of people who are, being very gracious with their time and who are helping me build certain aspects of Suborbital. But there's a whole lot that still needs to be done. And so I'm hoping to bring on more people to, work on the frameworks with me. And it's, I think it's important to have more people from the community invest their time and helping move everything along together. And yeah, so if anybody is interested in contributing to the open source projects of Suborbital, please just send me a message on Twitter. I'm at Cohix, C-O-H-I-X, or you can check the contributor guide in any of the repos.
Okay. There's a question here. I believe this is for Robert. Let me bring it up. So regarding the perf, 1 year ago I was searching the image perf regarding. Okay, I found that sometimes it's even faster than Wasm. Does this still exist in 2021? Any idea what the? It's about?
So yes. So I would say it's not always the case that using WebAssembly will be faster than JavaScript. There's a lot of use cases where it could be the contrary, and I've seen that as well. And yeah, it definitely depends on the application. Like, for example, one application in which you might not see improvement is if you have to do a lot of message passing between your JavaScript and WebAssembly code. And you're doing a lot of like, oh, I have the string, I want to convert it to an array of bytes so that WebAssembly understands it and go back and forth. You're going to end up with something that's going to be much slower. And in fact, that's how a lot of the performance updates that we've done have come about, is by doing the opposite of that, is by reducing how much data we're passing back and forth. So yeah, it's very much possible that the performance story in WebAssembly isn't as clear cut as we might want it to be.
Okay. Sorry, I'm just messaging Jay to see if he's going to be joining us soon. I'm sure he's going to be here very, very soon. Okay. I think there are other... Okay, no, it's the same person. So there are no new questions there. Okay, someone joined. It's Jay.
Hello.
Hi, Jay.
Hello. Hi, everyone.
Hi. We finished a little bit early, so don't worry. You're not late. We just finished a little bit early. Okay, so I believe we have Mitch, or maybe he stepped away for a bit. Hi, Mitch.
Hello.
Right. So we finished a little bit early. I guess we'll just get on with with the panel discussion. So to folks watching again, you can type in your questions, for the panel. But for starters, so maybe I'll ask each one of you to introduce yourself. Obviously, Robert and Connor just finished their talk. But if you just introduce yourselves again for people who maybe just joined. Let's start with you, Robert.
Yeah, sure. I'll make it quick since people have probably heard it. So yeah, I'm a bioinformatics software engineer. Very interested in WebAssembly for doing data analysis in the browser and in serverless functions. And that's about it.
Okay, yeah. And Connor?
Yeah, for sure. My name's Connor. I'm a staff developer at 1Password, and I'm the lead maintainer of the Suborbital set of projects. I mainly work on back-end development. I'm very interested in distributed computing, which is why I've decided to spend all this time working on back-end WebAssembly. And yeah, I'm really happy to be here.
Great. And Jay? So Jay and Mitch were speakers at our last event back in September. But Jay, yes, go ahead and introduce yourself.
Sure. Hey everyone, I'm Jay Phelps. I'm one of the co-founders at a company called Outsmartly. And my major interest in WebAssembly is just that I've been a long time compiler and language enthusiast, and I have experience in native and web. And so when WebAssembly came out, it was just a perfect combination of all of my passions.
Thanks for that. Mitch?
Yeah, sure. Hello, everyone. My name is Mitch Dickinson. I'm an engineering manager. I work at Shopify. I'm based out of Waterloo, which is about an hour west of Toronto. I'm leading a team within Shopify. Currently, we're building a serverless application hosting platform for Shopify apps. It's called Shopify Scripts. It's what I spoke about last time at WebAssembly Live. And yeah, there is a public, I believe you can find that talk on YouTube if you want to learn more about what we're doing. But yeah, I got into it just as a general fan of developer tools and building cool software. And I saw the opportunity within Shopify, and fortunately had the leadership around me to support the initiative, which was really great. And we've been working at it for about 2 years now. And it's going quite well. So it's been great to kind of ride the WebAssembly rocket ship and contribute back where we can. So I'm also excited to be here.
Great. Okay, a question for all of you. So why and how did you get involved with WebAssembly? Let's maybe start with Jay.
Sure. Yeah. So I've been, for as long as I can remember, I was really interested in compilers and languages and stuff like that. So I'm always tinkering on some sort of programming language or reading papers and researching and stuff like that, just because it's like jobs for those sorts of things are few and far between. But I've experience I've written native apps and I've also done web apps. So when WebAssembly came out, I was just very excited to be able to not only just use it, but also help people bridge the gap, because a lot of native people hadn't used a lot of web stuff, and a lot of web people haven't used a lot of native stuff. And so especially early on, I did a lot of evangelism, going out and talking and going to conferences and stuff like that, just helping people kind of understand what the pros and cons and what this really means and those sorts of things. So that was kind of my initial interest in it. Over the years, I have played with various custom languages, like one that I've spoken about in the past, Jaguar and stuff like that. But then I've also just used WebAssembly, just as a consumer, both on the web with various things, whether it be porting an existing, library that was written in C or C++, or writing greenfield stuff in Rust and AssemblyScript, and then also just on the server stuff with Fastly and other related serverless sort of WebAssembly infrastructure stuff. And I lurk on the community group as well, but I don't like. I speak up when I have particular input, but I let that ship pretty much drive itself.
Yeah, I kind of joined that as well. Because of you, you sent me the info about that, and I that's all I do. I lurk and I listen. I
It's
learn,
great.
from just listening. So it's great.
Mm-hmm.
And for folks who don't know, it happens every other Tuesday, as far as I'm aware. So if you're not interested in joining the community group, just ping any one of us, really.
Yeah, and the community group.
Oh, go ahead.
Sorry, Dan, I just wanted to explain. I don't know if the community group has been explained before, but briefly, it's essentially the community version of the standards body, like the people who are making the actual WebAssembly standards. This is like the community version of it. There's technically a working group, which is the actual standards body, but sometimes the community group is in control, and sometimes the working group's in control when it comes to like standards in general. In the WebAssembly world, almost 100% the community group is in control. Like the working group is almost a formality, at least currently. It's almost a rubber stamp after, based on the discussions of what actually happens in the community group. There's probably going to be exceptions to that as things grow and time moves on and more people come in and stuff like that, because it just will be, eventually the community group will just be unmaintainable. There'll just be too many people that just join, and you have to. But anyone's welcome. You do have to join the. I think you do have to join the W3C, which is free for an individual. But I don't know if that's still a requirement. I know it used to be, but.
Yeah, I think you have to create an account or something. That's what I did when I first joined. But it's a pretty straightforward process. So yeah, I encourage everyone interested in WebAssembly to go and explore how you can join the community group. Thanks for additional information, Jay. So getting back to Mitch, so why and how did you get involved with WebAssembly? Is it just when you joined Shopify, or were you already exploring it before that? What's
good question.
story?
I joined Shopify with no intention of learning about WebAssembly or getting into it. I come from a background working in startups, and I'm a big fan of just building cool products and solving problems in the world with software. Which after I had been at Shopify for a few months working on a product called Flow, which is sort of like a visual programming language for merchants to program their stores, I stumbled on to this other problem, which was around a product called Scripts. And Scripts had actually existed within Shopify for years before I joined the company. And with Scripts, a merchant running a store on Shopify could upload a snippet of Ruby code to customize the way that their discounts would run within Shopify's checkout. And it was a really popular product with our Plus merchants, and Plus being sort of the top tier of Shopify plans. And I started looking at the Scripts product and looking into the various problems that were sort of existent in that product, and there were a number of them, despite being successful in the market. And that's when we started internally talking about like what else can we do with this idea of allowing untrusted parties to customize our multi-tenant software as a service commerce solution in a secure way. And out of that came some of the initial explorations around, okay, well, what technology exists out there for running untrusted code? What sort of sandbox tech is there? What programming languages does it support? And we did a whole bunch of prototyping. And that's where WebAssembly came in. And it was sort of our early prototypes with WebAssembly, with some of the runtimes that were around back in, I guess it was 2019, early 2019. And we just had the performance numbers that we got were really great. We weren't seeing cold starts. We were seeing the latency values that we knew we needed to make our product successful. And that sort of is how it all started for us at Shopify. And since then, like I said earlier, we've grown the team. We've started really building a product, and now we're getting ready to sort of launch to the world. So it's really exciting what we've done. But that's kind of how I got started with WebAssembly.
Hey, Jen, you're muted.
Thank you for that. Yeah, there was probably with my sound earlier, so I tried to mute myself, not to cause any more problems with sounds. But anyway, yes, thanks for that, Jay. Connor?
Yeah, for sure. So I mentioned it briefly in my talk, but when I was initially developing the job scheduler that is now called Reactor, it was based on Docker, and the container is not the perfect vehicle for running low latency execution of functions. It ended up being quite a bloated code base. It was not achieving the performance that I was hoping to have, and so I decided about 4 or 5 months into building that project that Docker wasn't going to fit the bill here. I wanted something simpler and something that was going to actually achieve better performance. So I started researching WebAssembly. I had heard about these runtimes that worked outside of the browser. I didn't know a whole lot about it. Spent probably 1 or 2 months just diving deep into how it works and what the memory layout is all about, and how interactions between modules and their hosts happen, and learning all the nitty-gritty that needed to go into building something like this. I realized that it was going to be a big task to get this to be usable for the things that I wanted to use it for, but the performance that I was getting from it was just so much better, and the simplicity of the resulting framework was just so much better. You didn't have to deploy a dozen Docker containers to be able to execute the amount of workload that I needed. You could actually just have one instance with a couple hundred WebAssembly modules inside of it, and you could get similar performance to a cluster of a dozen or more Docker containers. So that's really why I started going down that path. And I've been working on this version of it for, I don't know, maybe 18 months or a little over a year, and I haven't regretted it. I'm quite happy with how WebAssembly is shaping up. I'm happy with how the community is moving it forward. Really great to see all the new projects that are coming up and all the new frameworks that are becoming available.
Thank you. Robert, how about yourself? You probably have a longer history with WebAssembly. You even wrote a book about it. What was the title of the book again?
Level Up with WebAssembly.
Okay, when did that come out?
Oh my. Maybe a year or two ago. I have a hard time keeping track of time lately.
No worries. I think everyone is on the same boat.
But yeah, I guess I've always been interested in doing more of the heavy lifting type of analysis in the browser. And before WebAssembly, I was just using JavaScript. But yeah, then one day I came across WebAssembly. It must have been, I think, one of Lynn Clark's articles, probably. And I was kind of surprised because it was such a good fit for bioinformatics, even though it was not at all built with that in mind. Because in bioinformatics, we have a lot of tools that are written in C, C++, and Rust. And so it's a pretty fantastic combination for then running it in the browser. And yeah, I think that's how I got started. And it honestly, the only reason I wrote the book was because I had such a hard time getting started with it as someone who doesn't have background in all these languages. And so yeah, I just wrote down the tutorial I wish I had.
Okay, very interesting. So talking about projects, you have talked about some project earlier and mentioned some things. But in terms of like real world, projects out there, are you working on anything that's currently really being used by consumers or companies? And also, if you're not actually involved with project yourself, do you know of any like real world applications out there that are heavily using WebAssembly and seeing the benefits of using WebAssembly? maybe we can start with you, Jay. I know you're playing around with a lot of like different things.
Sure. Yeah. Right this moment, I have some WebAssembly related stuff that we at Smartly that we're not ready to announce. But so other than that, I'm not currently on the stuff that I'm working on. Not currently working on anything, but over the years, I've worked with tons of different things, whether it's the stuff that I'm actually working on my day-to-day, or like I've also helped out, on a mentor and contract basis, other companies and stuff trying to move their stuff over. Like I had Stack Blitz folks needed help on moving some of the stuff that they wanted to run that was node-based, but over to WebAssembly. Various people, I mean, I can't tell you how many times people have needed image-related things that I've helped people with, image compression or resizing and those sorts of utilities. Trying to think of more notable ones. Yeah, nothing's immediately coming to mind. Just various stuff. I mean, like at some of the companies I've worked at, there's been there was one particular one. We had to make a DSL for this query language thing, for this custom internal thing. That ran on a WebAssembly virtual machine because it had more complicated stuff on it. It was not very simple. It was pretty complicated. Yeah, that's the big things at this moment.
Okay. And Mitch, obviously you're working heavily on in the Shopify, app application, all that. Are there any like big like milestones you're looking to reach with regards to development? On the Shopify side of things, using WebAssembly, or other projects you might be aware of that's heavily using WebAssembly?
Right. Yeah. So at Shopify, obviously I know of one project that's pretty real, which is what we're doing with scripts at Shopify. And I can share, like, we have not yet released our developer platform out there to the world in a beta capacity or general availability yet. That is those are some of the milestones we're working towards right now. And as far as I know, it's going quite well. I can share though that our infrastructure and our runtime environment is today in production at Shopify, serving a few use cases for real merchants around the world. So we've done a number of, now obviously we were the users of the developer platform in this context. Like we wrote the assembly script that ultimately, runs in production, but as a way of dog fooding the platform. And then I can also share, like, we've run some trials internally. Shopify is a really popular platform for a lot of large flash sellers. And so what a flash sale is, for those who don't know, it's and I might not get the explanation right, but it's, some celebrity or famous person has 100 pairs of sneakers and they drop them at exactly 11 a.m. on, this day, and half the internet wants those sneakers, and it results, and not only, humans, but there's also a massive market for like resale. And so that generates a whole bunch of bot traffic to acquire those products. And so anyways, Shopify has this flash sale problem where, our merchants can't come down when there are large flash sales. It's something that we value really highly at the company, and it's a competitive advantage. And so our platform has to run in this context. And we've actually had some really promising results with some recent load tests in the context of these flash sales, making sure that the platform that's hosting this untrusted code can essentially spike to many millions of requests per minute virtually instantaneously. So we've had some really promising data. I can't share specifics, but I'd say that in terms of performance scalability and the developer platform, it's been going quite well. And if you kind of follow Shopify's blog or our the release radar, hopefully we'll see some more stuff to follow in the coming months and years.
Mitch, can you talk about, I don't know if you can, putting you on the spot here, but can you talk about which WebAssembly virtual machine you guys ended up using? Yeah,
we're using Lucette. So we wrote our own glue wrapper around Lucette. So we use Lucette for the runtime, which the AOT function was the most important part for us. Like we compile ahead of time the Wasm binaries to machine code, and then we cache those in memory so that we essentially eliminate our cold starts and have near native execution time. Lucette did that really well. We've gone through a few historically. Like our infrastructure originally was using the Perlin Life runtime, which that was years ago. I don't know if that one's still around. Yeah, Lucett's been working really well. I'd say that we've architected to be able to swap in and out. I know like many people building these sort of frameworks have done the same, but as of right now, it's been working quite well for us.
Interesting. How about you, Robert? Any, with regards to applications that are out there, heavily using WebAssembly?
Yeah, so I mentioned a couple of them in the talk, but one in particular that I think is interesting is called Ribbon, and it basically does genomics analysis in the browser so that the user can load in local data and it will look at the data, without sending anything to a server, and does the analysis in the browser. Maybe another one I'll mention is not so much a web app, but a library. It's called Wasm. And sorry for all the bioinformatics references, but basically the goal is to have a repository of the most commonly used bioinformatics tools, pre-compiled to WebAssembly, hosted for free on a CDN that all these other apps can make use of.
Okay, interesting. Interesting that there are like other applications for it. Connor, aside from Suborbital, any other projects that you're aware of out there that's noteworthy?
Yeah, absolutely. I've built myself a bunch of applications using Suborbital. Of course, I'm using my own tools to specifically build analytics around my community, around the Suborbital open source community. And 1Password actually does use WebAssembly in our browser extension. So whenever you use 1Password to log in, we have a WebAssembly module that's analyzing the web page to figure out where the form is and which parts of your 1Password items should be filled into which fields and whatnot. But there have been a whole bunch of different applications that I've seen pop up over the last year or two. I think a really great one is Figma, the design application. It's using WebAssembly to accelerate the canvas that they're rendering. And I really like the Internet Archive using WebAssembly to run old Flash animations in a sandbox to be able to preserve Flash now that it's not supported in most browsers anymore. So there's definitely a lot of interesting applications out there in the real world, and I'm just seeing more and more as time goes on.
Interesting. Because of course, WebAssembly is quite young. Am I right in saying that it's only around for like 4 or 5 years? Is that correct, or am I wrong in saying that? Has it been around longer?
I don't know the exact amount of time that it's been around, but I believe the major browsers had good support for it sometime in 2018, early 2019, and it's only gotten better since then.
Okay, so it's fairly young. So for anyone who is just starting to look into WebAssembly or want to learn about it, what's your recommendation? Where should they start? Obviously, getting involved with community group is a good thing. As I said, I joined and listened, and I'm picking up some things. But obviously, that's just one aspect of it. Any pointers where people should get started with? Maybe start with Jay.
Sure. It really depends on what. Unfortunately, it's gonna depends on what it is you want to do with WebAssembly. If you want to be a basically, if WebAssembly, we're kind of in an odd point at this point. So like how many people, if you're writing a native app, how many people are like, oh, how do you get started in x86, or if you're writing a Java app, or you're writing an Android app or whatever using Java, how many people say how do you get started with Java bytecode? Of course, they don't say those sort of things, but it makes sense to say that today because we're just not quite there yet with tooling and with platform support, and things are still growing. It is somewhat of a trailblazing sort of thing. That being said, if you're trying to, so there's two major categories. You're trying to get into the tooling related stuff. So you actually want to know, you're trying to understand WebAssembly itself, build tooling, build languages, build platforms, those sorts of things. That really, honestly, you need to start at the spec. I mean, really, the spec is actually very well written, I think, and easy to understand. The spec website's pretty great at that and giving examples. Checking out things like Binarian. Binarian's it's a back end for generating WebAssembly. So if you're writing a compiler, write some sort of virtual machine or whatever it is, and you want to generate WebAssembly, Binarian's a great reference, and again, code's pretty clean, so it's really easy and good to reference. If you're more on the and then also LLVM has support and stuff like that, but LLVM, it's tough because it's like a monster. It's huge, and it's like really tough to get started. But there are the basics. There's something, the keyword you probably want to search for is kaleidoscope, which I could not spell for you off the top of my head. But the kaleidoscope, just try and search LLVM kaleidoscope, and that will give you various tutorials that are kind of infamous in the industry. But if you're trying to consume, like if WebAssembly is just an implementation detail for you, like you're trying to write in Rust and you want to just run it on Fastly's Terrarium infrastructure, which is like a serverless infrastructure at the CDN edge that can run WebAssembly. Those sorts of things, really, it's specific to the language. So Rust is probably one of the most infamous, like as far as support for WebAssembly. It's really, really robust. The core team cares about it, and a lot of folks in the community care about the support. So there's Wasm BindGen is one of the projects that they maintain for doing bindings and stuff like that, and they have pretty good docs. It is somewhat overwhelming if you're very new to Rust. Buckle your seatbelt, because it's still going to be like a tough ride, even though the docs do make some assumptions that you already are familiar with Rust and those sorts of things. But there's some some good tutorials. If you're a JavaScript person, which I imagine a number of people watching this probably are, as probably folks have mentioned in the conference, that assembly script is going to be your best bet for getting started. The syntax is super similar. Syntactically, it's actually identical to TypeScript. Semantically, there are some differences, but it's a really great way to get started. I think the assembly script website, it could use work, like most things, but it's actually pretty good going through those sorts of things. And it has I know for sure it has a really open community. The Discord channel, very open. All the core team and working group members are very, very happy to help you get started and stuff like that. So I'll leave it at that and let other people chime in.
Yeah. So Aaron Turner, who now works for Fastly, actually was supposed to join us today, but there's been some changes, with his schedule and all that. So I'm hoping that he'll be joining us, at future events. And he's as far as I know, he's the lead maintainer. Correct, Jay, for assembly script?
Aaron, he's not the lead, but
okay, sorry. So
yeah. That'd be Daniel, but he is on the core team and very active, and he helps organize the working group and community group meetings. So he does a lot, and it also does a lot of evangelism for AssemblyScript. That's why a lot of people think that he's the core maintainer. He's somewhat of the face of AssemblyScript in the sense of conferences and these sorts of things. He does a really good job.
And like Jay and Mitch, he gave a talk at the last WebAssembly Live event as well, so check that out. So maybe going to, Robert, any tips, for people who are new to WebAssembly, where they should get started?
Well, I think Jay's answer was very, very good. I don't have much to add to this. I'm a little biased. There are pretty good books out there on WebAssembly.
I'm sorry, I should have mentioned that. Buy Robert's book. There you go.
But there's one thing I found to be useful is pick a command line tool that you like that isn't too complicated, and try using that as a project and try getting through it. I would say if you come from a web development background, it's normal if it feels like really hard at first. Just stick with it. It involves so many new technologies, especially if you don't have that background. But that's kind of my recommendation.
And I would love to touch on that because Robert's point is great about that it can feel overwhelming. I think from the conferences and to people, I've talked to so many people who are interested and then they get overwhelmed, and there's a perception that it's harder than what they're used to doing. And I strongly disagree with that. I disagree. I mean, there certainly are things that are harder than the average web app, but the tooling is supposed to hide that stuff. And then there's cases where the tooling doesn't hide that stuff. But by and large, I think people don't realize that this native infrastructure and LLVM and Clang and Mscript and all this Rust and stuff like that, they feel like it's harder, but it's really just you're not used to it. And believe me, these native folks, they think the exact same thing. Well, not all of them, but a lot of them say and think the exact same thing about web. If they and if they don't, they haven't tried to actually build a modern web app, because if they did, they would realize that it is very difficult because they're just not familiar with it, right? So don't let that discourage you, is kind of my point, is that it's not that you can't do it, you're just not familiar with it yet.
Yeah, I guess it's true for anything, right? Because if you don't know anything about it, then it feels scary. But yeah, I guess take it in small bites and you'll get there. I think that's what I tell myself anyway. If I want to learn something new. How about you, Mitch? Any pointers you want to add?
Yeah, I don't think I can add too much beyond what's already been said. Maybe, if you're interested in building an app for Shopify, that's a potentially really great way to get started in WebAssembly. Not yet, but soon. And maybe make some money at it too, if given that Shopify does have an app store with a wide partner ecosystem. So there is real opportunity there that will be available to leverage WebAssembly. But besides that, yeah, I wouldn't add too much. Assembly script has been pretty good for us in terms of educating our developer ecosystem, who primarily come from web development and using a lot of JavaScript, a lot of dynamic languages. That's one of the main reasons we chose assembly script, and we found that the low barrier due to the familiarity of the language has been really helpful for the community of devs that we're building for. Now, that doesn't apply to anyone, obviously, who's looking to use WebAssembly, but if that is your background, assembly script, I would +1 to that. It's a pretty great language. Yeah.
Okay. Great. How about you, Connor?
Yeah, I mean, I don't have a whole ton of other advice to give. I think it's very correct that it really depends on the language that you're wanting to write and compile to WebAssembly. The tool chains are all slightly different. I'm coming at it from developing frameworks, and part of that has been building a little bit of tooling to make it easier to use the suborbital frameworks. So the Subo CLI tool that I demoed in my talk, I like to call it a meta tool chain, because it itself isn't doing anything. It doesn't have a compiler in it, but it is wrapping the tool chains for the languages that it supports. So the Rust and the Cargo tool chain and the Swift Wasm tool chain, it is helping you wrangle those underlying tools to invoke them in exactly the right way to produce exactly the right output. And it's kind of acts as a wrapper around the different tools that you would otherwise need to, learn all the command line flags and learn how to pass the correct, inputs and outputs to. So, in that way, I think Subo is actually a decent way of being able to compile WebAssembly, just because you don't have to learn all of the different semantics of the tools underneath it, but it doesn't support everything. It doesn't support assembly script yet, hopefully soon. And so, if you're like me and you like to go and learn the nitty gritty, and you like to know how all the different options and flags and inputs work, then by all means, there's a Rust Wasm book that you can go and look at. I think Jay mentioned, and walking through that will give you all the information you need to know about Rust, and the Swift Wasm website as well has some good tutorials on how to get started. But in general, just think about it from the angle of what you're trying to accomplish, and then just go down the path of whichever language or framework you're hoping to use.
Great. Thank you for those answers. I've got one question here from the audience. Let me bring it up. Can you share your experience with debugging of Wasm apps? Maybe we can start with Mitch.
Yeah,
you
sure.
described it.
Yeah, this has been one of our bigger challenges building a developer platform at Shopify. The tool chains and the runtimes is, to my knowledge anyways, and maybe one of the smarter folks here can correct me, but there's just a lot of missing components there from a developer experience point of view. Interactive debuggers, support for things like Dwarf across the different languages. So it's been a challenge, and it's one of our actually current bigger challenges, I would say, is building what I would say maybe is a modern developer experience on top of where WebAssembly is today. Debugging is a challenge. Access to standard libraries and tools that are out there is a challenge. There's not a ton of backwards compatibility, depending on which ecosystem you're in. I'm speaking more, with respect to assembly script. I think it's a bit of a different story. If you're in, say, a C, but yeah, back to debugging, it's been a challenge for us. And currently, we don't have a strong solution for this at Shopify. We're integrating some simple things like logging is where we sort of started, but we're still a ways away from sort of the full interactive debugger experience that a lot of devs might expect coming into a new ecosystem like this. So it's a challenge. I would love to hear what the other panelists have to say about this, though.
There's, the folks that I think, I haven't followed this very, very recently, so my information might be out of date. But the last I knew of it, and I do keep my ear to the ground, is that Chrome was kind of leading the way as far as the debugging experience. Ingvar, one of the developer advocates for WebAssembly at Google, added Dwarf support, I think maybe last year or a year before that or something. But it's preliminary and not entirely, it doesn't support everything at Dwarf, and there's gaps. And really fundamentally, it's just that the source map specification that was developed for JavaScript doesn't work well in some of these native languages. There's things that don't map well. And so while you can get the experience by and large that I've felt is that it'll usually take you to the right line, but beyond that, things don't usually work all that well. As far as your local variables and closures, and things get really complicated just because every language kind of has their different requirements. So it's tough. There was a working group specifically working on this. I don't know if they're still. I don't know if anyone knows if they're still active. I haven't heard anything recently. Sometimes these working groups kind of go off and do their own thing and then come back when they're ready. But it is from my perspective, at least every time I use WebAssembly in every context, it is an open problem. You do end up, it's one of those things where it's if you are used to debugging low-level stuff, like debugging low-level WebAssembly or even debugging low-level, if you're writing C++ especially, where you're used to looking at memory addresses and all these sorts of things. If you're used to that sort of thing, then you probably won't be that big of a deal. If you're new to that, it definitely, you can feel some pain. But there's different techniques. There's case-by-case basis. If you're developing a library, and you're using if you're using Rust or C++, which can target multiple environments. One thing that some people do is they literally just target a native executable, and then they just use GDB, the normal built-in debugger that they're used to using, for stepping through that code, and then they just switch targets. They switch to WebAssembly target when they go to the web. But that's not a tenable solution in the long run.
Robert or Connor, any additions to that?
Yeah, there's definitely been more print debugging in my recent past than probably I've seen before. Similarly to what Mitch said, logging was the first thing that I implemented when I was working, because you kind of need it. If something's crashing, you just got to put some logs in there to figure out where it's crashing and what's happening. But I do think that this is something we'll see improve pretty quickly. I'm hoping a year from now we'll have a much better story once all the tool chains, are speaking the same language. That language would be Dwarf. And I agree with you, Jay, that the Chrome team is definitely leading the way there. I've seen pretty consistent updates from them that are making debugging with WebAssembly easier. And I know the Swift Wasm team is working on it as well. I think it was touched on in talk earlier. And so, you know, we're not there yet. Yes, it's an open problem, but you know, it's something that can be solved, and it is getting there.
There's actually a question here for Mitch specifically. Let me just bring that up. Okay.
Cool. So yeah, the question is, Mitch, could you elaborate a bit more on what you had to do to support a few million requests per minute? Sure. Yeah. I mean, a couple things. Like I mentioned that we ahead of time compile all of our modules to machine code, and we cache those in memory. So whenever a request hits our system, it's hot, it's there, it's ready to run. One advantage to our platform is the scripts that get written are, you can think of them as little snippets of business logic. So typically these modules are very small, at least with our current state. So we're only talking a few kind of 100 kilobytes. We don't typically see very large WebAssembly modules. And that's a function of, you know, we're using assembly script, which is one of its like good characteristics is it produces pretty small binaries. But also like the type of programs that people are writing on our platform are sort of naturally pretty small. So we can fit a lot of these modules in memory on a given worker in our infrastructure, thousands, tens of thousands potentially. And from there, like the rest is just good old fashioned horizontal scaling. Like we run a lot of servers that are hosting this runtime. We have a load balancer in front that's routing to, you know, all the different servers that are online. And currently, because our platform doesn't have any sort of statefulness, like we're only working with pure functions, it makes that fan out horizontal scalability like a much easier problem to tackle. If all of those modules were reading and writing to like a shared database or something like that, it would be a much different story. So I would say like there's no secret magic there. It's a function of WebAssembly itself, especially when you have a small module, is pretty efficient. And the types of programs that people write on Shopify are small, and we're not opening up sort of a lot of risk associated with accessing external systems. So we also do a lot of caching. I should have said that too. So those are some of the things we've done. I would say there's no, it maybe sounds impressive when you read it, but it's just good old fashioned horizontal scaling, like I said. More servers, more money.
You're not giving you guys enough credit. It is impressive.
Okay, thanks, Jay.
That's great. Okay, I don't think there are any more questions from the audience. But are there any like specific things you want to talk about, maybe about your company or your other projects before we wrap up? Jay, it might not be exactly related to WebAssembly like 100%, but you want to just talk about what you're doing at Smartly?
Sure. So yeah, I mean, we have some stuff under the hood that WebAssembly I can't talk about, unfortunately, at this point. Sure. But the other stuff we're doing is the related to compilers and stuff, static analysis. We analyze your React code, and we're able to do code slicing where we extract out the minimum amount of JavaScript that would be required to re-render a particular prop in a React component. We have a couple talks on that kind of go into that. I would say, as far as kind of like from my closing perspective, the thing that I really enjoyed when I was first learning WebAssembly is writing WebAssembly by hand. Like it's like, you know, just using what's called S expressions, which is essentially like just parentheses. It's just like Lisp back in the day, where people still write Lisp. And honestly, I feel like it was a really enlightening, easy for me to like, you know, it's not the easiest thing in the world, but I just mean that like it kind of demystified it. Whenever I've shown that to people, like I've shown it to people, quite a few people, just walk them through it. And it's hard maybe to do on your own without having someone walking you through it. But I don't know, Robert, does your book do any of the S expression stuff where you're writing some WebAssembly by hand, or is that too low level for that book? Oh, wow. His audio is messed up for me. Is it messed up for everyone else?
It is.
Sounds like you're a robot, Robert. Robert the robot.
We had it earlier.
Yeah, it's messed up, unfortunately. I can't. What did you say?
I had that same problem earlier.
Oh, yeah. I'm sorry, Robert. But I imagine it probably doesn't because that's fairly low level. But it's pretty. I think it's pretty easy, even especially if you ignore loads and stores. Like if you're trying to load and store numbers from memory or something. If you ignore that for a second and you're just talking about locals, I think you'll be like, oh, this is kind of like JavaScript or something. You've got like these local variables, and you can just set them and get them, and you can return them. Especially if you're using the AST form of the S expressions. I think it can help you demystify and be less intimidated. It'll also help if you're debugging and you don't have source maps or dwarf or any of this stuff to understand some of the little basics of how it works.
Okay. Robert's probably going to be coming back. So I'll bring him in when he does. There's actually one more question here from Min. Let me just bring it up. Why not, right? Let's take this question. I don't know who to answer this, but is it possible to write server code using assembly script that makes use of I/O?
Yeah, for sure. So I don't know how much WASI was really discussed today, but WASI is the WebAssembly system interface. It allows you to do certain I/O with the host. Reactor, like my suborbital projects, I've extended WASI to give additional capabilities to it as well. And I am working on assembly script support. It's coming soon. I know Mitch and his team have done some work with assembly script. You're not allowing access to things on the host by design because you don't want people uploading untrusted code and executing whatever they want on Shopify servers. But there is the Wasm Cloud project. They use a library called WAPC, or WebAssembly Procedure Calls, and that does have assembly script support, so you are able to do calls between the host and the guest using assembly script, and I'm sure there's some others out there, but it's definitely possible. It's just not necessarily built right in. It's something that needs to have a little bit of additional glue code added around it to make it really work properly.
Yeah, at Shopify, we use a library called AS-WASI. I can link it in the chat, but this is the tool. It's a assembly script layer for the WebAssembly system interface, or WASI, and we use this at Shopify, I believe, for our logging, which is currently our platform, the only I/O sort of feature we support is sort of a basic logging, and that's how we did it, was through this AS-WASI. And I believe we had to write some glue as well around it. I'm not entirely sure about that, but I can double check, but this was the tool we used.
Okay. Anything else from anyone with regards to that question? Okay, I guess not. So I just want to again thank every speaker and panelist who joined us today. I'm hoping that we will be able to do a lot more of this event around WebAssembly. So I started this conference last year. It was supposed to happen back in March, but obviously things started locking down and all that, so we had to postpone it to September. And the reason really why I'm interested in WebAssembly is when I was starting to code, do my first job at Citigroup, there was a person who was working on the assembly language, and I wanted to learn it, but I was like so busy with other things. I wasn't like part of that team and all that. So, it's like a frustration. I didn't learn it then. So now I'm trying to kind of get involved with it, another way by being part of the community. I'm not sure if I'm really gonna like learn it, as deeply as I would like, because I'm not really gonna need it for a project right now. For those who doesn't know, I'm actually retired. I retired very early from my career, but I've always been interested in things that are like new in tech, and I try and keep myself up to date. So one thing I can do, for WebAssembly really is to build, events around it, and have wonderful speakers like yourselves. And yes, and also thank you for companies who support initiatives like this. One of them is let me just share sorry about this. So one of them is Bloomberg Tech, who supported us from the very first event. And Outsmartly also is a sponsor. And Second State, which has Tim McCallum as an engineer, also supported us for this event. And I'm sorry about this. So yeah, thanks again, Outsmartly and the Second State. And I just want to mention Jonathan Berry of WebAssembly in San Francisco. He actually helped with some of the speakers, for today. And in the past, Jay, I know you recommended a lot of speakers for the first event as well. I know you recommended Mitch. That's why we had him for that first event, and now we have him here again. So thanks again, everyone. Any last few words or tips from you folks before we wrap up?
Just get started and try something out. Is the only thing I would say. It's really quite fascinating and fun when you get into it, and it opens a lot of doors for different new paradigms for software development. So just try it out and get started.
Anyone else?
Connor said it best.
Yeah, great. So I think on that note, we're going to wrap up. And thanks everyone for joining us today. And as I said, we'll try and create more events around WebAssembly as sort of a service to to the WebAssembly community. And if you want to know more about future events, just make sure that you check our website, which is webassembly.live. We'll be posting, future events there, and we're gonna try and coordinate with other WebAssembly communities as well, like in San Francisco, and I know there's some in Europe as well. There's one in London, which I kind of inherited from the person who started it, who incidentally is the one who actually designed the logo for WebAssembly. So that's very interesting. And thanks again, everyone, and enjoy the rest of your day. And thanks, Jay, Robert, Connor, and Mitch. Enjoy your day.
Thank you.
Take care.
Thank you.
Bye, everyone.